Good morning and welcome back to day 3 of the Software Engineering Institute's research review, the 2021 version of our virtual research review. Very glad to see you all back here with us today. I think we have a really exciting day teed up for you. We are doing a lot of collaborative conversations today. So we have 3 large sessions of collaborative conversations, kicking off this morning with one on human-centered AI, moving into AI fusion for a collaborative conversation later this afternoon, and sort of finishing up the day with a conversation on the future of software engineering. The focus of today is really trustworthy AI ML, but more broadly, AI engineering and the future of software and the future of software, cyber, software, and AI going ahead for the next 10, 15, 20 years. So today, you're really going to get a better picture of where we go into the future. This is part of our study portion of the mechanism we've talked about several times already and how we do our work. This is much more of the how do we really get that latest cutting edge work in AI, in cyber, and in software, and really use it to drive the agenda for all of the out years. I think you'll find it a really nice bookend from the keynote that we had from Ms. Heidi Hsu on the very first day, and the priorities moving ahead into the research for the future, and where we're going with regard to the future of the SEI and our collaboration with all of you moving into the future. Collaboration, clearly that important element of working with you to establish all of this for the future. So I encourage you today, as you think about what it is that you hear, what it is that tickles your fancy a little bit here, think about reaching out and collaborating with us in the future in terms of where we're going. So that's all I'm going to do. I'm going to get ready for today as we go out. We also have some detailed technical briefs on train but verify, AI engineering, in an uncertain world, and predicting inference degradation in production ML systems. So these are also going to be very, very good detailed technical briefs that you'll have. You won't want to miss those as we come into today. But let me go ahead, and after the moment when we return, we're going to introduce our first collaborative conversation. This one is actually going to be led by Carol Smith. And let me just talk for just a moment about Carol. Carol's a senior research scientist in the human-machine interaction. She's a senior research scientist with the Emerging Technology Center, now the new Artificial Intelligence Division at our institute. In this role, she contributes to the research and development focused on improving user experiences and interactions with the nation's artificial intelligence systems, robotics, and other emerging technologies. Our MC today, for the rest of today, as we go through, is Tanisha Smith. And she will be joining you after the collaborative conversation to help introduce the rest of the day. Please enjoy the day, and I'll see you for the wrap up at the end.
Hello, and welcome to our collaboration conversation on human-centered artificial intelligence. I'm joined today by Alex Van Deusen, our design researcher in the AI division, and Jared Dunnmon, technical director and AI ML portfolio lead at the Department of Defense Defense Innovation Unit. And I will let them introduce themselves. Alex?
Hi, thanks, Carol. I'm Alex Van Deusen, and like Carol mentioned, I'm a design researcher at the AI division at the SEI. I have a background in communications and visual design, and I've been facilitating meetings and workshops on a variety of topics for about 3 years now. Part of my focus is in aligning research and business objectives, which often means facilitating conversations and listening to problems that our collaborators have and considering how we might go about setting out to solve those problems. And oftentimes we have these really intricate, interesting solutions that could be complex and difficult to communicate. So I also focus on developing ways we can showcase our work and demonstrate our impact. I'll let Jared introduce himself.
Wonderful.
Thanks, Alex. My name is Jared Dunnmon. I'm the technical director for AI at the Defense Innovation Unit. And what I spend my day doing is thinking about how we can leverage commercial technology to better support the national security community. And what that means is really thinking about how we identify and curate problems in the DoD and across the broader security community that could benefit from commercial technology, making sure that the technical fundamentals that underlie those problems are consistent with what can be delivered on a reasonable timescale from the commercial world, and then working to help manage the technical aspects of program execution, test and evaluation, and these sorts of aspects. And so we work with a number of colleagues, obviously on the commercial side, on the defense side, and we've been really lucky to be able to engage with folks at the SEI as well to think about some of the broader issues and some of the broader questions that we wrestle with on a day-to-day basis doing this. And Carol and Alex have been one of the core parts of our team at DIU for a bit. So we're really excited to be able to be here with them.
Yeah, no, thank you so much for joining us. It has been a pleasure to be able to work with you. And today we're talking about human-centered AI. And this is an area that has been talked about for many, many years across a lot of different ways of talking about it. So within user experience, within human-computer interaction, and within AI engineering. And the SEI has defined human-centered AI as one of the 3 pillars of AI engineering. And Alex, could you tell us a little bit about human-centered AI?
Yeah, absolutely. So yeah, like Carol said, human-centered AI is one of those 3 pillars of AI engineering we have at the SEI. And our focus on human-centered AI has to do with effective implementation and minimizing unintended consequences of AI capabilities. So there's 3 kind of things we look at when we're talking about human-centered AI. We think about context of use. So what is the desired outcome and the human needs that we're addressing? Designing for human machine teaming, thinking about how people interact with the system and how do they understand what that system is doing. And then the last thing is engaging critical oversight, which is about asking important questions like, what are we doing and why are we doing it and who is it for? And this really is about identifying risks of bias, misuse, abuse, and proactively identifying unintended consequences.
Excellent. And I'd like to first just dig into that idea of the context of use and the complexities that can be there. We always want to spend that time to make sure that we're solving the right problem and who we're solving it for, and making sure that it's going to be a system that they are able to understand and interact with in the ways that they need to. But what changes between regular software and AI-enabled systems with regard to that context of use?
I would say there is quite a lot of differences. There is an extra layer of thought and consideration that has to go into AI-enabled systems. And because we're still learning as we go, we have extra work to do when we start using AI capabilities. But AI systems are dynamic, and they should be thought more of partners rather than tools. And when we think about deploying AI capabilities, we kind of have to recognize that the real world operational environments in which teams and organizations are going to be embedding those AI systems are dynamic and complex, and they have ambiguous decision spaces. So in high stakes scenarios, humans and AI systems have to work together in human machine teams with trust, ethical integrity, and mutual understanding of a shared goal.
Excellent. Jared, did you have anything to add on that?
I think Alex's description is pretty apt. I would just say that the biggest challenge, or the place where we spend the most time in developing these sorts of systems, is exactly that, is not just understanding, well, I have a system that I want to build and I can write a program and be confident that it's going to deterministically do exactly what I expect it to do. What often happens is I'm able to build a mathematical approximation of some complex process that I care about. And the question is, how good is that approximation? When does it fail? Does it fail in places that I care about? And how can I design a co-workflow between this approximation here and a human, so that I can best assist that human in the tasks that they're doing, without creating risk for substantial downside. And the fact that a lot of these systems don't have deterministic and complete test surfaces, like some software systems, is, I would say, kind of a high level functional difference in how we have to approach them.
Yeah, no, that's a great point. Yeah, and particularly we've seen a fair amount of AI systems, particularly with regard to image recognition, where they're not learning the right patterns necessarily, or people are applying one system that works in one situation, in one context, to another context or another situation that wasn't intended to work in. And then we have those failures that you mentioned. Yeah, that's wonderful points from you both. So how, when we think about those changes in context that can occur outside of the system as well as inside of the system, but when systems are being used, particularly in situations where weather might be a concern. So if it starts raining and the situation is deteriorating, thinking about the systems working within that situation and teaming with the humans and understanding the context. And another scenario is thinking about data, either that the system or the human has brought from other sources, and how to share that information, and considering that change. And then the classic situation of just some, the vehicles running out of gas, or some other completely, not that it's not normal, but it's definitely a situation where they need to react in a way that wasn't necessarily part of the mission. Either of you have any other ways that we should be thinking about those changes in context and how to manage those between the human and the machine?
Yeah, I think you covered a lot there. I think that, like Jared was saying, it's really thinking about how does the human work with a system that's designed to do one thing, but when it faces changes in context, how does it react? So it's really about getting the desired outcome and the human needs, and aligning the understanding of that. So did the human and AI understand when shifts in context have occurred, and can we maintain clarity around the intent of what we want a system to do, and how do we adapt and evolve based on contexts that are ever changing, like when we have complex environmental contexts or different human factors, or even just a lot of information that a system is accepting and trying to understand and work with. So yeah, there's a lot of different things to think about when we're deploying an AI capability.
Excellent.
Yeah, and I would just follow up by saying that there's an organizational component to this as well, which is that often an AI system is supposed to be used or intended to be used within some process, as the internals of some process, or to speed up some process, or to improve some process within an organization. And if that is done, one often has to think about what that new combined workflow looks like between the computational system and the human actors that used to perform that task. So what that means concretely is, maybe I have 100 analysts performing a task today. Tomorrow, what that may look like is I'm automating some part of that task, that workflow, and then I have 10 of those analysts doing quality control on top of that, on top of a particular model, and I have the other 90 who are doing that for, say, other models that I've built. and to allow myself to do more analysis than I was able to do before, because I'm able to make better use of those human resources. And so there's an organizational reframing that sometimes has to happen here, where it's not just a matter of shoehorning a computational object into an existing workflow, but rather there's some thought that should probably go into how the organization fundamentally is structured and what those functions are the human beings are performing. And that part of the teaming is something that is I think requires answering some sometimes hard questions up front about really big organizational changes that are required to make best use of these types of technologies.
Yeah, excellent point. It makes me think also about the idea that these systems can somehow fix organizational problems, which unfortunately is not something that they are capable of doing. The human problems that we have to be fixed first prior to putting them an AI system of any type. Something that Alex had brought up earlier was the idea of trust and transparency, and thinking about what the appropriate level of trust is between a human and a machine when they're teaming, and how much someone should be trusting the system. I think, and often people think that they should be able to trust the system 100%, and that skepticism that is required is often dismissed, but I do feel that that's a significant part of a successful human-machine team, is making sure that the humans are still understanding the limitations and the capabilities of the system and having transparency into that, so that their trust is appropriate with regard to that system, and not overly trusting or under trusting either, to the point where they wouldn't be willing to use it. What other considerations should we be thinking about with regard to human-machine teaming?
Yeah, I think what you just talked about, having the ability for a human to understand why a machine is making that decision, is super important for when we're trying to build trust between the human and machine. And I also think that there's kind of some things we can do to think a little bit harder about what a machine might be doing, and what those unintended consequences might be. So there's lots of different user experience research and human-computer interaction methods that we can use to kind of think about, let's think really hard about what might go wrong and what might be something we need to put in place. And so things like performing abusability testing. So what if somebody was intentionally misusing a system, or flipping it to test it. So if we flip the situation and something feels weird about that, or just unnatural, then we might have uncovered some kind of bias that we didn't normally know. And you can also have your team take something like an implicit association test, which reveals bias in different associations. So those kind of things are, I would say, another consideration to kind of go a little bit further when we think about how we want to interact, have the interactions between humans and machines, is thinking, what if this doesn't go the way we want it to go? Exactly.
Excellent. Yeah. Jared, did you have anything to add there?
Yeah, and this will, I think, hit on one of the question I just saw in the chat, which, to some degree is, what does software for an AI system need to include or manifest to help enable that trust? And this is maybe a drum that I'll beat repeatedly, but a lot of it is a matter of thinking about verifiability, and that's a term that has meanings to different folks. And in this context, what I mean is, given a system output, can I convince myself by some other mechanism, be that a model that is explainable in the sense that I see the prediction, I see what came out of it, and I can look at, say, if I'm doing linear regression, like the simplest version of simplest versions of an automated system, and I can look at the statistically significant coefficients, and I can say, okay, well, here what's contributing here, and I can look at the coefficients that went in there. I can look at the the data point that I put in and say, okay, well, this coefficient contributed this much, this coefficient contributed this much. All right, I have a sense of why this prediction was the way it was. That's one method of verifiability, but it's not the only one. So, for instance, if I have an anomaly detection algorithm that is running over, say, millions and millions and millions of documents, I can go and do, or a better example is make millions and millions and millions of satellite images. And one option is to have humans review, every single one to try to look for the anomaly. That's which is just kind of not feasible. The second option is, well, I have a machine learning system do this, and I tune it so that recall is very, very high. So I'm pretty confident there aren't going to be many false negatives, but maybe there are a bunch of false positives, and that can be, and assume in my task the false positive is bad. Taking an action on a false positive is results in a bad thing. And so what I can do is say, well, my recall is high, but my precision is only 10%. So it means, like, 1 of every 10 things I review is actually a false. Only 1 of every 10 things I review is actually a true positive. So there are a couple ways I can do this. One thing I can do is say, well, okay, well, I've got, maybe I've got 1,000 predictions that I'd have to review, and a human could theoretically just do that themselves. So I kind of reduce the human workload. That's one thing. So you're putting the human in, in the loop in the right place. A second thing to do would be to say, okay, I've got my predictions from this machine learning system. I'm now going to use dual phenomenology. So I'm going to fire another satellite at this, another type of sensor to see if I can find this anomaly on another type of sensor and confirm it using another type of sensor. And then I say, okay, well, I've now seen this, kind of being predicted from this machine learning system, and I've confirmed it using this other phenomenology. I'm pretty confident that that's true. And either one of those approaches, be it use dual phenomenology or kind of human review of a reduced set, or even again building a model that is explainable in some sense, can help give the human operator confidence. And yes, in fact, this is excuse me, my outputs here are correct and actionable. But it does require, and then going back to the drum that I'm going to continue to beat, it requires co-design. It requires thinking about the context into which one is deploying that algorithm. It requires thinking about the level of performance I can get. So for instance, if I cannot get something that has really high recall there, and no matter what I do, I'm only at 80% recall, maybe I'm really worried about those false negatives, and I've got to augment this with another complementary diagnostic or something. And so just to zoom out, this issue of algorithm human co-design is probably the most important part of these systems, there's a number of different ways you can surface information to convince a human that yes, this is in fact true. So for instance, if you're looking at documents, you can often surface, if you're looking at building knowledge graphs, you can, for instance, if you have an edge that you're looking at, say, hey, why is this entity related to this entity in this way? You can have a system that actually surfaces the source document and says, okay, well, this is the thing that contributed. So that level of, again, to some degree, accurately and rapidly exposing evidence that can lead to a quick confirmatory analysis is something that is really useful and really important in practice. And the last thing I'll say is that people have to drill with these things. So if you're particularly in the security community, if someone gives you a new thing, you're never going to use it in real life unless you're convinced that it's going to work and do the thing that you expect it to do. And the only way that happens, particularly, it's one thing if you're the person with the capability in your hand. If you're a commander, it's different, because you may not have ever drilled with that on your own, but you need to have actually gone through exercises where you have leveraged the output of that thing, even coming up through your chain of command, to make a decision and to understand, okay, this is how this can go sideways. This is how this can work well. And understanding those nuances is something that's really important. So this is all just to say at a high level, and Carol, I'll get off my soapbox in a second. This is all just to say at a high level, to build out these systems effectively, they can provide an immense amount of value, but there is a cost associated with all of this packaging and all of these things that you need to design around it. And it's something that folks should be aware of and cognizant of as they decide whether building a machine learning system for an application, for instance, is actually worth their time and effort, versus building, say, a more deterministic system that has flaws, but then they can but those flaws can be mitigated at a lower cost than kind of building an AI system with all this packaging around.
Yeah, no, excellent points. And I think you're alluding as well to that baseline, like are things currently being done? And is the system really performing in a way that is actually improving that? Or, and if not, is it, again, to your point, is it worth it? And abandoning projects as early as possible is something you've brought up quite a few times. If it's not the right solution, not falling for that sunken cost fallacy, but rather, really looking at what is the right solution here and how can we help people to do their work more effectively. Yeah, excellent. So I thought we could spend a little bit of time talking about responsible AI, which is a part of human-centered AI, and the work particularly that the DIU has been doing with making systems to help people to do responsible AI. I thought it'd be good to just start with what we think of, what the three of us think of when we think of responsible AI. Alex, do you want to kick it off?
Yeah, sure. Thank you, Carol. I think of AI and responsible AI and all of the work that's going into, that area as a way to take ownership for the AI capabilities that we design. So we really need to be thinking hard and asking the really tough questions that need to be thought through in order to make AI solutions that are safe, ethical, and secure. And so, like I said before, these are dynamic operational environments. And when they need to work in those environments, we need to think through the consequences of unintentional or intentional misuse, abuse, unwanted harm. So that's a lot of work, but it's also really important to do the best to design these systems, to do our best and think through all of those different parts of it. And that's how I think of responsible AI.
Nice. Jared, anything to add?
Yeah, just a lot of the systems that we build in this area are effectively leveraging mathematical approximations of a human process, and they're imperfect. Sometimes they're in some ways functionally superior to what humans can do, whether that's speed of reaction or kind of say the resolution of perception, these sorts of things. But at a high level, it's important to understand exactly how those systems can and will behave. And it's important to even more so to be able to say that any mathematical model, any mathematical process makes some assumptions that underlie that mathematical model. And for AI systems in particular, one of the failure modes that I've commonly seen in practice, and that's kind of spanned academia, industry, and in some degree in government, is the assumptions that underlie the development process at some point were not true during deployment. And that can look like a shift in what the data set looks like. That can look like a shift in what the output label ontologies for a classification problem look like. That can look like the task itself being kind of overcome by events and no longer useful. And so the responsible AI, in addition to what Alex said, which I think is on point, I think there's a aspect of this process of developing a system responsibly that, particularly because they often don't have, it's really difficult to have complete test surfaces for all these systems. It's important to be very explicit about exactly what assumptions went into it. And to say, what are my assumptions about how the task is currently done, the baseline, what in a practical sense, what do I need to be? Because again, if the way that we're doing it right now is terrible and we can provide a little bit of, we can do it mediocrely, that may be an improvement. Mm-hmm. What are the assumptions about my data? Do I always have access to it? Well, do I understand its provenance? Am I positive that it's relevant? Is it representative? All of these, what are the, and kind of given those things, what are the possible error modes of a system like this? What are the possible costs of each of those error modes? And these are things that, you would say, well, that's just systems engineering. That's not AI specific. And I would say to you that you're right. But I would also say that because of the particular way that these models are built and the highly variable set of failures that they can have, it is important to be very explicit about what those costs are and what those potential costs are and what those assumptions are, so that when we go to implement a system in practice, we're very clear about exactly what those trade-offs are and exactly what trade-offs we're choosing to make. And folks can choose to, I mean, in reality, in real life, people take risks all the time. Risk management is a part of life. And so, it's I think it's unrealistic to expect a system to be perfect, like it's unrealistic to expect almost any system to be perfect. But that's why it's important to co-design it with the workflows you're working in. And to be able to do that, you have to express and make explicit these assumptions and these costs. And one of the work that we've done with Carol and Alex and at the SEI has really been working on thinking about how can we have those conversations with potential users, across axes of technical and non-technical, senior to non-senior, program managers, DoD folks, commercial folks, make sure everybody's on the same page when we're talking about what those trade-offs and costs are and how we plan to mitigate them, so that we can make effective and risk-informed decisions in deployment.
Yeah, no, and your point about the inability to make perfect systems, I think, is really important. There's that bias towards automation that people tend to have, and the assumption that somehow math will mitigate all of that complexity and make things better. And in many cases, it just propagates the existing problems and really makes them even more powerful in some ways, elevates them to broader sets of data. And the data we build these systems on was, of course, created by humans who are imperfect in many, many ways. So yeah, realizing that the systems aren't going to be any better than we are is I think, a really important point. Wonderful. So the Department of Defense over a year and a half ago, adopted the ethical principles for AI, which include responsible, equitable, traceable, reliable, and governable. And I thought it would be a good time to really think about how those relate to what we're talking about today, human-centered AI, and specifically, Jared, how you're operationalizing the ethical principles at DIU. And I know that the report is very, very soon forthcoming, but if you want to talk about that work, I think that would be great.
Sure. And Carol, Alex, feel free to jump in. You all know a lot of the detail here as well. The short version is that when the DoD released these principles in early 2020, at DIU, we're constantly working with running rapid acquisition programs where, again, we're matching kind of commercial capabilities with problems in the security community. And an immediate kind of set of questions we got from the vendors we work with is, okay, I see these principles and they make sense, but each of them is a couple of sentences. Like, what do they mean that I actually have to do? Like, how do I convince you, the DoD, that we're building something that aligns with these principles? And I think that's not an easy question. It's not an easy question. Again, this is kind of a topic of ongoing research. There's certainly not a perfect answer to that question. But what we tried to do at DIU with again, partners at SEI, folks from industry, folks from government, folks from academia, is really to think about, all right, how would we, in the process of managing specifically kind of the types of acquisition programs that DIU runs, provide at least some sort of guidance on a process by which we might be able to convince ourselves that we're building systems in a way that align with those principles. And by no means, to preface all of this is not the answer. This is a best working hypothesis that we look to continue to improve with kind of the partners that I mentioned earlier. But it's really breaking down the development cycle into a couple of different buckets. So first there's kind of a planning stage where you think about what is the context for this system. So what is the task it's doing? What are the metrics by which you measure success? And what's your current baseline? If we can't answer those three questions very precisely, we're going to have problems down the line in deciding in being able to express exactly what risks and what trade-offs we're making. Secondly, data, provenance, relevance, access, all of these things that are critically important that, again, are often assumed. But when you go brass tacks and say, okay, give me access to this data, you might get an answer that says, oh, well, I can only get you this part of the data, not that part of the data. And it fundamentally changes, whether you think this is a good idea or whether or not you can build a functional system. There are pieces then about making sure you identify end users, stakeholders, who are all of those folks, and then using that as input into kind of explicit harms modeling exercise to say, how could this go wrong? And if it goes wrong in these ways, what are the costs? And then, finally making sure, and particularly in a public sector setting, making sure that the accountability structure is clear. Because there will be someone, for instance, who's responsible for performing a particular mission or a particular function. And ultimately, that's the person of the organization that's going to be helped by that capability, and would need to make decisions about, should we deploy this or not. There's a second phase here, which is development, which is focused on things like, have we considered guarding against unintended manipulation of the data or the model, making models, making it clear what the structure for third-party auditing is, making it clear again who has actually responsibility or the accountability to decide, yes, we are going to make change X to the system or not. And then really asking questions about, what do we need to be thinking about in post-deployment monitoring? What are the questions we need to constantly be asking? And then once we get to deployment, we want to have had this conversation about how we're doing continuous harms analysis. Like, what does it look like? What's the frequency on which we're doing it? What is the process if we find something that's not what we expect? Is there a process, for instance, for system rollback? So I have version 2.0 and it works mostly better, but we found a flaw. Okay, we need to be able to roll back to 1.9. If we don't have that rollback process to 1.9, that's a problem. Mm-hmm. And then being able to, again, make sure functional testing, make sure that the thing is still, that the task is still valid in the context of the overall, organizational workflow. And all of these things are, again, high level concepts that you would think, yeah, okay, this makes sense. But the purpose of a lot of the work that we've done was to, with kind of those collaborators I mentioned, was very much to try to make this instead of a checklist that says, like, you need to have done all these things, 90 pages of checkboxes. Here's kind of at least a vaguely linear process that you can follow to say, here's a set of lines of inquiry that we can follow. And if we've had these conversations and we've documented why we did what we did, at the end of a capability development cycle where we run a prototype before, and we have to decide whether these prototypes have been successful before we authorize them to go into production to actually be used. We can approach the process of writing that success memo that says, this is exactly how this succeeded, in a very concrete way, to say, here is exactly, the risks we considered, here's exactly how we did this, here's exactly how we expect this capability to be used. Here's the documentation associated, here are the model cards associated with it. Mm-hmm. And be able to then communicate that trade-off space very clearly to operational folks, and then be able to make kind of risk-informed decisions about how to use them. So that's really the work that we've been trying to do and trying to prototype on a number of our programs, and we're very grateful to particularly some of the commercial partners that we're not obligated to do that work by contract, but really stepped up and helped us to try to prototype that. So we're very appreciative for those folks.
Yeah, no, it's been wonderful watching this whole work progress. And we did have a question of the audience about model cards, and certainly that is an important part of this work, as are another related paper on data sheets for data sets, and really thinking thoroughly about the work that's being done and why those decisions are being made, and being able to explain exactly how these systems work, providing that the details and really opening the doors to the system so that it is not opaque, so that we understand how it works and why it's working the way it does. Because we do not, certainly to a broader audience, particularly want to expose people to systems that we don't understand ourselves. The people who make the system and who operate the system certainly need that transparency to understand the details of the system so that they can monitor and improve it as needed.
Yeah, and I'll just say, the explicit reference, I mean, the reference to kind of Mitchell, Gebru et al. Like, yeah, I mean, that's that line of work. So not just the model cards, paper and the stuff associated with that, but kind of downstream work in this area, everything from, the questions about large language models and what do they learn, yes, and how should we be addressing those issues, all the way down to, hidden stratification, which, where you have problems where you have labels that are too coarse, and so you have failures within those label sets on subclasses that you didn't label. There's all the way to things like downsampling attacks, where you have images, and then you downsample the image and it starts looking like something completely different after you preprocess it. There are all sorts of different failure modes that one has to think about. And the line of work that's referenced there is like, this is absolutely critically important. Again, not just, and I'll make this point, not just from a responsibility standpoint, which is extremely important, but also from a functional standpoint. Like if you have something, the thing that I constantly say, like if you have a biased model, it is not just a bad thing from an ethical standpoint, potentially. It is a bad thing from a functional standpoint, because it means that you have a model that does not work on subset of your data, and that is generally not a good thing.
Yeah. Great. So we only have a few minutes left. Audience, if you do have questions, please make sure you get those into us so we can address them. I'd like to just talk a little bit about the collaboration that we've had. We're having a collaboration conversation here, and we have had the pleasure of being able to work together for almost a year on the DIU's Responsible AI Guidelines, and then other smaller projects. And I thought you both could share a little bit about what that's been like for you. What have you learned?
Yeah, absolutely. I think it has been great. The collaboration has been great. We've been really able to do a deep dive and get into what these DoD ethical principles mean for our work, and the people who are going to be using AI capabilities. So I think it's been just a great experience to see how we can actionize those things. We look at them kind of as aspirational goals to work toward, but they're also something that we can coalesce on and say, well, we're agreeing that we want to aspire to these certain principles. And they become tools for conversation. And it's a tool that helps you be able to say, well, have we talked about this? And those ethical principles can help you frame your work and talk about potential harms and mitigation planning and all of that kind of stuff. But I think it's really nice to have explicit permission almost to consider the depth and of implications that might be things that go wrong and things that we should think hard about. And those ethical principles are great because they help us say, this is what we're working toward and this is what we want to know. And as Jared mentioned, we took those principles and then asked questions at each stage of development, from planning to development to then deployment, and all along the way trying to make sure that we are always working toward achieving those things. So I think it's been an awesome collaboration. It's been so fun to just think about how are people going to work through these really tough problems.
Well said. Yeah, no, it's been such a great partnership. Did you have anything to add, Jared? We have an audience.
Just that we're incredibly grateful for the work that Carol and Alex and others at the SEI have done here, because the time that you all spent taking some of the initial raw ideas and then helping form them. It's like, all right, so if we want to actually have a human being interact with these ideas, we need to have here are ways that we can think about doing that. Here are ways that we can think about making this accessible, and here are ways that we can think about even iterating on, again, like the kind of a user-centric design of even the way that we're communicating these things is an incredibly important aspect of this. And it's something that within kind of when I would say the DoD proper, there aren't all that many folks that spend their time thinking about those things to the level of detail that you all do. And so it's been both extremely helpful for us, but also great learning experience as well to learn from watching your process and seeing how we can do a little bit better on our end as we kind of take that and think about how we work in other areas as well.
Yeah, no, I'm all for raising expectations. People shouldn't have to put up with bad user interfaces or anything else. They shouldn't have good experiences. Life is hard enough. So we do have a good audience question that I definitely want to dive into. So what's the difference between human-centered AI and explainable AI? And explainable AI is really loaded because there is a DARPA project titled Explainable AI, XAI, which tends to influence how people think about a very generic term, explainable. At its best, an explainable AI both is understandable to the people who are working on it, to the people who are updating data, who need to do some training to maybe make changes to the model. They really have a good understanding, because the information is available to them, of how the system was built, why the system was built, how it's supposed to work, and those types of aspects. And then on the user side, on the people who are intended users of it, they also have the information that they need to interact with it at their level. So there are two different experiences that we're talking about with explainable AI. And it's really important to know that those can't be the same. An end user typically is not going to understand if you show them the algorithm that was used to create this piece of information that came through the system. That's not explainable to them. They need information that is applicable to them. So they need, as Jared mentioned earlier, that the actual paper that was sourced, or the reason that this decision or this recommendation was made, and what data it was based on. So it is very human-centered to make an explainable AI, but usually with explainable AI, they're talking about two completely different audiences, which I think is confusing, unfortunately. Anything to add, either of you?
No, I think you did a great job covering. That's great.
Yeah, I will say I think it is a common misconception that one can only build a human-centered system if you have an explainable system. There are ways to design workflows wherein I can leverage a black box, and if I've got dual phenomenology or human review on the back end of it, I can still make great use of it. And because I have designed it around the workflow that the human is doing, there are ways to that you can design those workflows in ways that account for the fact that you may not be able to peer inside the model and kind of understand from first principles why it's making a particular prediction. But you can post-process it with a human-driven workflow in a way that's useful. So I think the one thing I would say is I think there's a common conflation between those two things, that we need to be careful when we design systems that where it is difficult to go to follow that path directly from a kind of human parsable set of features to an output. But I think there are increasingly ways to do that, and the degree to which we can do that will certainly define the degree to which we're able to extract value from AI systems in a responsible way, kind of in practice. And there's no prior on that. It may be the case that you will only be able to do that once in a while. It may be the case that we'll find ways to do that, a large portion of the time. So just to point that out.
Awesome. Well, thank you both so much. This has been a wonderful conversation. I look forward to hopefully more chances to collaborate with you both. And thank you all very much. Thank you to the audience too. Great questions.
Hi, I'm Nathan VanHoudnos, Senior Machine Learning Research Scientist at the SEI. My talk will highlight exciting research the SEI is conducting in collaboration with our partners at Carnegie Mellon University to advance the field of AI engineering. In particular, I'll discuss our latest work on Train but Verify, a multi-year effort to develop an AI engineering process to train AI systems to have specific robustness properties, along with the testing framework capable of verifying those properties. I'll also present Juneberry, a framework we've developed for our own research that aims to improve the reproducibility of machine learning research and evaluation. We've made this tool available for you to use in your own research, and I look forward to telling you more about it. So please, join me on Wednesday, November 10th at 12:05 p.m. Eastern for more insights on this line of research.
Bringing all those people together from different places and different ideas really helps us form perspective, but it also helps us then spawn innovation across the community, right? We kind of become the seed or the germ of the innovation, and working with people over time, right? Whole industries are born.
We get great new ideas when we try to work across divisions. I think we get great new innovative ideas when we work with members of the software engineering communities and through our professional societies.
We have a collection of incredibly talented folks in their respective fields. And it's not just the researchers, as great as they are. It's the folks that do all the things that enable the researchers to do their jobs. We have some of the best and brightest in the various disciplines we all serve.
I support SEI staff by providing information that they need. I mean, we're not doing the technical work, but we're trying to understand it to the point where we can provide the resources for the technical staff to do their work. We learn a lot about the terminology, and it makes us better when we're developing search strategies.
Knowing that we have an SEI family that is made up of people from diverse backgrounds, educational backgrounds, cultural backgrounds, I think brings a lot to the table when you're tackling really hard problems for our sponsor.
Good ideas come from really bright people. And interestingly, one of the things that inspires me and keeps me focused on the work of the SEI is all of the really smart people we have here.
Robustness is a key consideration when engineering AI systems. Ensuring robustness, however, is a challenge in many tasks due to the inherent uncertainty in the environments in which AI systems are deployed. Motivated by this, our work focuses on quantifying, characterizing, and mitigating uncertainty in machine learning models, which are often at the center of AI systems. In this talk, I'll discuss our work on a particular formalization of quantifying uncertainty known as classifier calibration. More specifically, we focus on how to evaluate machine learning classifiers for their ability to express confidence in their predictions according to definitions of calibration that map to application-specific contexts. We show that standard metrics for evaluating classifier calibration often do not measure the quality of confidence estimates with respect to important events, trade-offs, or use cases that are important to practical usage of the classifier. We then derive metrics that directly measure calibration performance in such contexts and compare a variety of the state-of-the-art in classifier calibration according to them. Equipped with these metrics, machine learning practitioners can evaluate their classifiers in such a way that more closely reflects the setting in which the classifiers are used. As a result, they can understand how robust their models are within mission context.
If you had to pick one practice, one goal from this list, where would you start?
I'm going to let you go first.
Well, certainly from the, again, I'll tie this back to some degree to the insider threat work that we've done here at CERT. Establishing the appropriate level of privileges that individuals need to do their job, it's critical. It is an arduous process to keep up with the access controls, but it's essential to be able to provide the minimum level of privileges needed for an individual to complete their job and activities. And that does extend to your traditional employees, but also your trusted business partners, contractors, subcontractors, suppliers. Again, tying that back into knowing what assets people should have access to and verifying that only the people that should have access do have access to those assets and the capabilities that are associated with that asset.
Okay, so Randy, you would start with access control. Matt?
These are all like my children, right? So I worked with the folks that built this. So asking me to pick a favorite, number two.
Well, if you've had siblings, you know there typically is a favorite.
Yep, and that would be me. So I would say identifying and being able to respond to risk is the most important thing. I need you to be able to frame risk for your organization, because that actually feeds just about everything else, right? How to build an incident response plan, you need to understand your risk appetite or risk tolerance. So if you're building a risk management program, being able to prioritize your risks will allow you to understand what sort of events are escalated to an incident response. It also lets you know how much network security and monitoring and so on and so forth. So I just feel like as if you understand your risk, you will be able to inform the other 10.
Yeah, so I'm going to start with the first item on the list. And I agree, all of these things are very important. And there's no right or wrong answer. But from my perspective, if you don't understand what the mission of the organization is, you don't understand the assets, you can't apply the things you've described.
Agreed.
So I think for my dollar, I would start with understanding the mission and assets of the organization, understanding that the interplay of these things is ultimately what we're looking for. Right? There's not one that's going to bring you cyber resilience. It's really doing this in a way that's coordinated, that's integrated.
I think the field keeps reinventing the Wild West, and because of that, the SEI needs to keep reinventing the discipline to corral the Wild West a little bit and bring some maturity to these technologies that are transforming everything.
A new idea for me is probably a new way to communicate something. You know, what's the best way to help somebody communicate what it is they're researching or explaining?
For me, new ideas come from Susie Miller. And the thing that I find inspiring is that she'll have a germ of an idea, and I get to collaborate with her. And the two of us working together is something better than either one of us could make by ourselves.
Those basic building blocks are what we could build innovation on, right? Getting everything organized and, leaves room for innovation, leaves room for growth.
The positive way to build on new ideas is to build them on top of a structure that you know is going to work and is not going to fall apart under stress.
Sometimes adding that structure or adding that process, that's the innovation itself. And that's the thing that takes a good idea and then makes it more workable. It's just not one person working on it themselves, but suddenly a bunch of people can do it.
I would say the research review is one of those events that highlights the innovation at the SEI. So I think in my day-to-day work, I tend to have my blinders on and I'm working on the projects that are in front of me. I don't really get a chance to see what everyone is working on, but at the research review, that shines through, like all the innovations that people have made, and it's kind of fabulous. It's awesome to see the work that people are doing.
Hello, my name is Tanisha Smith, and I'm a technical manager in the Artificial Intelligence Division of the Software Engineering Institute at Carnegie Mellon University. Today, I'm very happy to introduce you to our researchers here at the Software Engineering Institute. If you have questions outside of our Q&A sessions, please feel free to contact info@sei.cmu.edu to reach me or any of the speakers. To kick off the next section of the 2021 research review, let's discuss trustworthiness in artificial intelligence and machine learning. There are many takes on trustworthiness, its definition, and its importance. However, I think the first step in developing trustworthy solutions is understanding intent, or more specifically, design. In April 2021, SEI hosted a podcast on designing trustworthy AI. It featured Carol Smith, Senior Research Scientist of Human-Machine Interaction, and she was interviewed by Suzanne Miller, Principal Researcher at SEI. I found this talk to be very interesting and insightful, and reference highlights from the talk to express this topic. So let's dig in. In the context, what does trustworthiness mean? At its most basic level, it is the ability to help people to understand why a system is making the decisions it is making. What information is it using? But really, the first step is very early on in the process, before the first line of code is written. The development team needs to think through the breadth of the work that they are doing and to be speculative about the potential negative outcomes, as well as the good outcomes, and to really think through the potential positive and negative impact so that they are better able to protect and empower people, and ultimately to build trust. Providing control and transparency will also enable the design and development of trustworthy AI ML systems because the technology will be built for people's needs and with human ethics. Trust is having the confidence in positive outcomes that a person willingly gives control to another party. Why is trustworthiness important in AI and ML, or artificial intelligence and machine learning? Ideally, AI and ML systems are actually augmenting our intelligence and helping us to be better at the work that we are doing, while allowing us to be better and utilize the skills that we have as humans to partner and to collaborate. I believe this was touched upon in the last session. Developing trust with people is critical to AI and ML adoption. People should always feel that if the system is not doing what is expected, that they are able to control the system. This could be shutting it off or having some other mitigation tool to control the system. As context and the confidence and evidence changes, there is a corresponding change in trust. Confidence is based on evidence of benevolence, integrity, and ability. It is important to understand the breadth of AI and ML responsibilities and also where its limits are, and making sure that it is understood by the people using it as well as the organizations that are getting data from it. It's really important to regulate to some extent what it is. We should not pursue 100% trust as a goal. Rather, people should always be somewhat skeptical of any system, any computer system, any experience that they're not sure of, and use their own knowledge of the situation and consider that option in making choices. Ultimately, it is critical that we establish what is called appropriate trust, a prerequisite to AI adoption, because trust is complex and, quite frankly, very personal. So by really understanding, then sharing how this system is drawing conclusions, we provide insight and help people to better partner and to trust systems. More, we can help them to be more successful because they will be able to partner more effectively with AI and ML systems. This brings us to our next talk. Let's dig deeper into AI and ML trust and verification with Dr. Nathan VanHoudnos. I'm going to talk a little bit about who Dr. Nathan VanHoudnos is. He's a senior machine learning research scientist at the Artificial Intelligence Division of the Software Engineering Institute at Carnegie Mellon University. He is primarily interested in helping to develop the field of AI engineering from its current Wild West state to a field with defined and repeatable processes that can be optimized. His current research focuses on training neural networks to be robust to post-training evasion attacks, and more generally, to verifying that a given neural network conforms to a defined set of security properties. Today, Dr. VanHoudnos will speak on Train but Verify towards practical AI robustness, an exciting collaboration with our academic partners at Carnegie Mellon University. As he mentioned earlier, this is a multi-year development in AI engineering with a focus on training AI systems to have specific robustness properties. With time, he's also hoping to talk about something called Juneberry, a framework we've developed for our own research that aims at improving the reproducibility of machine learning research and evaluation. Please welcome Dr. Nathan VanHoudnos.
Hello, thank you for joining us. My name is Nathan VanHoudnos, and I'm here to talk to you about Train but Verify. But first, a word from our lawyers. This basically says that everything in this presentation is publicly releasable. So before I start explaining about Train but Verify in this particular project, what I want to do is I want to kind of come up a couple of levels. And I want to introduce this concept of AI engineering. AI engineering is a field of research and practice that integrates a lot of different pieces of expertise: software engineering, systems engineering, computer science, human-centered design. And the idea is to build AI systems that are responsive to human needs and mission outcomes. Why do we need a field of AI engineering? Well, some research that's been done suggests that about 85% of AI deployments will in fact fail. And the reason that they'll fail in some sense is because people are making heroic efforts to solve problems, but they don't have a defined and repeatable system to make sure that they can achieve their goals and understand how to avoid failures. So that's AI engineering. It has 3 different pillars. One of them is human-centered, in that it works with and for people. Another is that it's scalable in terms of both very large models and very small models at the edge, and also that it's robust and secure, which means that it's reliable when under uncertainty or threat, right? And train but verify is in fact about threats, right? What are the threats to machine learning models, and how do we make sure that we can overcome those threats? So let's talk about threats for a minute. When I like to introduce machine learning threats to people, I like to think of the Beeler taxonomy, which is basically saying that an adversary can make a machine learning component either learn the wrong thing, do the wrong thing, or reveal the wrong thing. And what I've listed under here for the different pieces is that for learn the wrong thing, what you have is the original Badnets paper for label poisoning. For do the wrong thing, what you have is this idea of like a facial recognition system that then if you put on glasses that are specially designed, you can fool that facial recognition system, so you can fool it in operation with an adversarial example. Or revealing the wrong thing, where after you have a trained model, you can back out characteristics of the training data. In the specific example, what you have is you have person Z extracted out of the model, and you can in fact see that those are the same person. Okay, so those are roughly the 3 different threats. So in the train but verify project, what we do is we think about it a little bit more broadly, right? We want to make sure that we can train to enforce a learn policy. We want to make sure that the systems learn the right thing. And then if we train to do that, we want to go ahead and verify that they did learn the right thing. Similarly, to make sure that they don't do the wrong thing, to not be fooled by adversarial attacks, right? Then we need to verify that they are in fact not fooled by adversarial attacks. And similarly for reveal, right? And there's a lot of work that focuses on a single security policy at a time, where if you're checking against data poisoning, you're going to verify that you weren't poisoned. If you're checking against robustness to adversarial examples, you're going to verify that your adversary can't actually fool you in practice, right? If you're checking that you're not revealing secrets, or if you're trying not to reveal secrets, you're going to check that you're not going to reveal secrets. But what if you need to do 2 things at once? So for example, the DoD makes high-stakes decisions and also trains on sensitive data. And so what about this cell of this train but verify grid? So it's been known for a long time that defenses for do policies reveal information about the data. So for example, in the original Cypress et al. Paper, where they showed that adversarial examples against robust models end up looking like instances of the class that is being targeted, right? We've known that these robust models might be leaking information about the training data. And so to explore this a little bit, let's just look at 2 models, a standard model, and then a model that's trained with projected gradient descent, right? And so on the y-axis, what we have is accuracy, and on the x-axis, what we have is the strength of the attacker, as the attacker is allowed to add more and more and more noise, their perturbation budget. And so what we see here is that standard models, as soon as you add a little bit of noise, their accuracy just craters, right? And then it just stays bad as you add more and more noise to the model. Robust models, however, more gently and smoothly degrade, but what happens is now the adversarial examples end up looking like the target class. So here, they begin to look like ships. And so what you can do is if you take a model that's been trained on ImageNet in a robust way, and then extract these adversarial examples, and just kind of move from class to class to class, what you get is this video on the top, where what we have is we have adversarial examples that are revealing information about the training data, because these things actually, in fact, look like the different classes, right? Like that's the alter class, for example, and it looks like, sure, those look like alters, and the dogs look good, and the insects look good, and all of that kind of thing, right? So we're actually leaking information about the training data. In contrast, examples extracted from undefended models look basically like noise. And so what I want to do next is I want to just sort of meditate on this idea of what information can be revealed by a model and sort of walk you through it. So imagine that, well, so not imagine, this is in fact the example from the stingray class, right? What we see here is we see what looks like a stingray, it looks like a stingray pattern, it's in the water, and then we have this object over here, which looks maybe like a swimmer in the water. And so then if you go into the ImageNet training data, you can in fact find lots and lots of examples of people in the water with stingrays, right? So here's the adversarial example for cauliflower. And I look at this and I'm like, the colors might be wrong because the cauliflower is purple. But of course, actually, if you're more of a foodie, you'd know that there is in fact lots and lots of purple cauliflower, and it's in fact very well represented in the ImageNet data set if you actually go into the data and inspect the training data itself. Right? So you can learn things about the data by looking at the adversarial examples from robust models. Let's give a more in-depth example. So let's look at the street sign class. So here's the adversarial example for the street sign class. And I look at that and I say, that looks maybe like E10. Okay, let's go to Google Maps. Let's throw in E10. Oh, it looks like E10 is in New York. There's actually a whole bunch of stuff in New York. Let's go to Google Street Maps view. It looks like that. That looks like maybe a New York style street sign. And if maybe you thought it was E70, same thing happens, right? So then what we can do is we can go into the data set and we can see, yes, there are actually quite a few photographs with these New York style street signs in the data, right? So we're revealing what kinds of, in this example, street signs are present in our data by looking at the adversarial examples. Okay, so let's make this a little bit more concrete for the DoD, right? If we're going to have AI engineering, and specifically we're going to have secure AI engineering, then what we need is we need to defend from multiple attacks. And the problem here is that state-of-the-art methods to enforce doing the right thing can leak information about the training data, right? Here are some examples of the aircraft carrier class and the submarine class, right? That are revealed in the robust model but aren't revealed in the standard model, right? And so what I want to point out here and argue for is that a defended model may, in fact, unintentionally reveal critical information about the data, specifically its sources and its methods, right? So to give a very sort of open example, right? What if we wanted to keep confidential that the way that we collected the information for a particular class was from personal photos, right? So that's with the stingray stuff, we train our defended model, and now our adversary is able to find out that there were people in the training data, right? A characteristic of the sources and methods of the data, right? And so organizations with high-stakes systems trained on sensitive data need new defense methods. We need to make sure that we can do things correctly and to not reveal secrets, okay? That's basically right where the train but verify program is. And what have we been doing up in 2021? What we've been doing is we've been trying to quantify attacks to reveal policies, develop new methods for due defenses and due attacks, develop new methods to verify those policies, and also release AI engineering tools, right? Because where we're eventually going with is that after we can better measure how information is in fact leaked, right? And we have the state-of-the-art for how to defend against doing the wrong thing, right? Then we can actually give some advice about how to both not leak information and do the right thing, which is our goal for next year. So what I'd like to do is we've got a lot of papers under review. I'd like to go over our ICML 21 paper on globally robust neural networks as a sort of a deep technical dive. This work, the first author on this is Klaus Lino. You'll see his picture at the end of the slide, or at the end of the deck. Okay, so globally robust neural networks. What are we talking about? So first, let's think about we have a model. Let's just call that model F, and let's define this local robustness condition, right? And so what's happening is that if you have some piece of data in pixel space and you draw an LP ball around it, right, that has radius epsilon, as long as it's far enough away from the decision boundary, at least epsilon away, then it has to have the same classification, right? So it's locally robust if decision boundaries don't ever cut in to LP balls. And that's how like Madry's adversarial training works. That's how trades works. That's how a lot of things work, is they try to penalize this idea of crossing a decision boundary in an LP ball. Okay, now that's really low level. That's really zoomed in. So let's zoom out for a minute, right? And let's think about a notion of global robustness, right? And so what I've drawn here on the slide is I've drawn this sort of half-moon spiral data set where we've got some dark things that curve around like this. This is one of the classes. And then we've got some lighter stuff that curves around like that. That's another one of the classes. And then we have a classifier that's trying to pick between those two colors. And the way that we drew this particular classifier is that it has a super, just really thick decision boundary. And we'll talk about that in a second, right? And so the way that you can go from local robustness to global robustness is to basically say that everything is locally robust, or the model refuses to comment on what class it is. And that's why the decision boundary in this case is so thick, because it can't certify that this particular instance definitely belongs in this class. Okay? That's how you make, that's the sort of conceptual idea for a globally robust neural network. The way that we ended up training these things is actually relatively simple. And so I want to kind of explain the intuition here. So let's imagine here that I give my neural network a piece of information to classify. It classifies it, and it splits it into between 1 and 4 classes. And I'm just looking at the logit scale. Okay? And so I can see that class 1 has the highest value, so the classifier thinks that it's class 1. Okay, so the next class down, right, is class 2. And the claim that we want to make is that if the margin between those two classes is large enough, then a small change in the input, right, an adversary adding a little bit of noise within the epsilon ball, is not going to allow class 2 to surpass class 1. It's that little bit of noise isn't going to be enough to close that gap. Okay, that sounds fine. How do we actually make that happen in practice? So there's this formal idea of smoothness called the Lipschitz constant that tells us how much things can change when you have small changes in the input, right? And it's been known for a while that robust models are actually smoother, right? So they have smaller Lipschitz constants, right? And so if we can make a model that's robust, we can drive down the Lipschitz constant enough that we can actually say things like this, right? That it's not going to change very much. A small change means that it's going to go down the top class is going to go down just a little bit, and the other classes are going to come up some. But if we add those things together, it's not going to go past it, right? And so we add this new class, which we call the bottom class, which reflects the highest score an adversary can get relative to the top class. And so now what you can do, as long as you do the two things, you make sure your model is smooth, you quantify how smooth your model is, and then for a small change, you figure out what's the worst it could be, and then you just train your model to drive down that bottom class, right? To make sure that it's always classifying correctly. Okay, so how well does this work? Basically, it works pretty well on 2 benchmark data sets. We're either exceeding or matching the previous state of the art. And that's good that we're doing well, but that's not really where the technique shines. Where the technique shines is in terms of its performance, right? So the GloRNet certification and training is significantly more time and memory efficient than other methods and far more scalable, right? So it's taking far less time and it's taking far less memory to actually do. And so that suggests to us that we'll be able to push this beyond these sorts of very simple benchmark data sets that are often used for certification research and into larger data sets like ImageNet that is future work. Okay, so that was our little science piece where we dove into that particular paper. The next thing that I want to talk about is I want to talk about some of the tools that we've been developing and that we've released. Specifically, there's a tool called Juneberry that we've released recently to GitHub. So what's Juneberry? the idea of Juneberry is that it provides a framework for reproducible machine learning research, right? The idea is not to have yet another framework that makes you go fast. This one is a framework that lets you go carefully and reproducibly, right? And so it improves the experience of machine learning experimentation, because now things are far more reproducible and I can dial in on the different pieces that I'm trying to do, right? It's extensible for a variety of machine learning tasks. And the way that it basically works is that we have all of these different adapters for the different pieces, the different backends. So we support PyTorch, Detectron2, MM detection, and TensorFlow, right? And the idea here is that what you can do with Juneberry is you can make a table of results more easily for your papers. And so some of the documentation that we've released includes this vignette where we replicate a classic machine learning result, and it walks through how we're going to load the data, how we're going to build a model factory so that we can take some machine learning component that exists and bring it into Juneberry, how we can in fact fill out a config to replicate a training strategy from a paper, how we can train a model, evaluate a model, and then how we can change the little pieces in the config in a full factorial experiment or other experimental design if you want to implement that, and just literally get all of the results and have your little table of results, right? And additional vignettes are coming for other pieces. Okay, so to sort of come back, the DoD needs secure AI across multiple policies. Train but verify is taking two of those, doing the right thing and not revealing secrets. And the idea is that we're going to allow for the use of high stakes, or we're going to allow for the use of sensitive data in high stakes environments. What we've done this year is basically a lot of pushing the state of the art and understanding how we can measure how much information is leaked and releasing some tools. And next year, what we're going to do is we're going to develop training methods for do and reveal that either enforce both of those policies or have a principled trade-off between them, as well as releasing additional tools. I'd like to close the talk with a sort of slide that shows the team. We're a big team. There are a lot of folks that have done a lot of work here. I specifically just called out the PIs, myself, Andrew Mellinger, my co-PI. He's sort of the guiding force behind Juneberry. Three of the professors on campus, Leo Bauer, Matt Fredrickson, and Brian Parno, as well as a collection of additional technical staff and students. So thank you, everyone. I hope you enjoy the rest of the day.
Welcome back. We are now with Dr. Nathan VanHoudnos for the question and answer session for Train but Verify towards practical AI robustness. Welcome. Welcome, Nathan. So we have some questions coming in. It looks like the first question is, do robust models leak instances of the training data or information about the training data?
That's a really good question. So in the original model inversion paper, what was going on is that they were sort of leaking information about all of the instances in the class at a single time, right? So these are in some sense canonical pieces of information that are leaked by the training data, or the canonical pieces of information about the training data that are leaked. So the security aspects of this are when different parts of the model are memorizing pieces of the training data that you don't necessarily want them to memorize, and it's leaking those different properties of the training data. It's not that specific instances are being leaked over time.
That's interesting. We have another question. If I wanted to use Juneberry, what do I need to do next?
Sure, that's a wonderful question. I'm glad that we have some people who are excited about this particular software tool. So Juneberry is publicly released. It's open source. You can find it on the CMU SEI GitHub. And basically you can just you can clone it. You can spin up the Docker container that it sort of says in the Docker file, and then you can just get started. A good point of entry for people is the vignette that we wrote replicating a classic machine learning result with Juneberry that will go through all of the different pieces from getting started all the way down to producing results from an experimental table in a paper.
So we just got actually another question. On one of your slides, you showed GlowRonet, I think I'm saying that properly, versus other methods according to some metric, VFA, I think. Can you speak to what the metric means?
Sure, so that's verified robust accuracy. The way that this works is that you need to measure your accuracy based on the specific pieces that you can say, oh, it belongs to class A, or oh, it belongs to class B. Not everything, because sometimes the classifier says, I don't know. That's part of the method. And so we have a measure of accuracy that takes into account for that.
Thank you so much, Dr. VanHoudnos. We have to wrap up, unfortunately, but thank you for your time for this Q&A session.
Glad to be here.
Next up is Dr. Eric Heim. Dr. Eric Heim is a senior machine learning researcher scientist at the Artificial Intelligence Division of the Software Engineering Institute here at Carnegie Mellon University. Dr. Heim's research focuses on practical issues of applying machine learning methods to real-world environments. Such issues include data scarcity, model robustness, learning from structured data, and enabling models to express and reason about uncertainty in their predictions. Today, Dr. Heim will speak on knowing what you don't know. Robustness is a key consideration when engineering AI systems. So in his work, he is trying to ensure robustness. However, it is a challenge and it requires many tasks due to the inherent uncertainty in the environment in which AI systems are deployed. Today, Dr. Heim will focus on classifier calibration, or more specifically, how to evaluate machine learning classifiers for their ability to express confidence in the prediction according to definitions of calibration. Thank you.
Hello, my name is Eric Heim. I'm the principal investigator on this project called Knowing When You Don't Know, AI Engineering in an Uncertain World. This project started last year, so we're in our first year. We just finished our first year, and we'll continue for the next 2 years. So at the core of this project is this idea of uncertainty in model predictions, specifically ML model predictions or machine learning model predictions. And we argue that quantifying and reasoning about this uncertainty is a key component for informative and robust AI systems. And so I'll be using this example throughout this talk of a object detection at the ground level, specifically of vehicles, motivated by some of the applications we have here at the AI division. But honestly, you can think about a lot of the concepts that I'm going to talk about today, not just within this application, but with many others. So if you have questions at the end of this, please feel free to ask me about how this work applies to your particular missions, or if you care to think about not this application that I talk about it or some other, please feel free to do so. But in this particular application, we have something, say, a autonomous ground robot that's doing some surveillance of some area. And for this particular task, it's common for an ML or machine learning model to do is something called object detection. So an ML model will make a prediction such as this, where it localizes or predicts the position of an object denoted by this bounding box here, as well as what this object is, the class of this object. In this case, it's a friendly truck. And such a prediction can be useful for intelligence analysts for predicting where potential assets or enemies are in some particular mission that feeds to some analysts to do some analysis. And while this is pretty informative, it can make predictions and inform such intelligence system or intelligence tasks, but it provides a very definitive statement about what the model thinks is reality. And what's potentially more useful in this situation is this idea of not just expressing what the class of that object is, but its confidence. So potentially more informative to an analyst is not just that the class is a friendly truck, but how confident, on a scale, in this case, from 0 to 1, of that prediction that the model is. And so considering that this friendly truck, this model is predicted with confidence, this model predicts friendly truck with confidence, say 98%, is very different than, say, around 35%. And this is something that the analyst can consider when considering the next steps in their task. And so that's why we say that accurate estimates of these uncertainty estimates from of machine learning model predictions can lead to better informed decision making. But that's not the only thing. If you look at the larger context of an AI system for which this machine learning model may be a component of, you can consider other usage of uncertainty. Specifically, if you consider not just the ML model's predictions going directly to an analyst, but to say give some situational awareness in some larger system depicted here by this map, where in the bottom left-hand corner, there's this triangle that represents the robot that's facing the road here. You can imagine a similar model being able to inform in such a way. So for instance, the model may be able to make the prediction, again, that there's a friendly truck that's detected in a location. And by doing so without understanding the confidence of this, it could say with definitive statements about reality that the friendly truck is in this location, say on this road. But again, this is fairly limited. But if you consider confidence, you can actually do different things. So for instance, you could threshold the confidence in such a way that if the confidence is over some threshold, such as 0.5, what you could say is, yes, we are confident enough about the prediction that we can say that this is a friendly truck at this location. But if you're not that confident, if you're below that threshold, you could say things like, hey, we know there's something on this road, but we're unsure about this class. And to gain confidence or to reduce uncertainty, you can then maneuver the robot to gain this idea of confidence, to get a better view of this, or task other sensors. So this is why we say that allowing higher level reasoning in AI systems access to this model predictive uncertainty, these systems can be more robust to the failures that are caused by unconfident predictions. So in this work, we focus on evaluating, characterizing, articulating, and rectifying uncertainty in machine learning models for the purpose of more informative and robust AI systems. Specifically in this talk, we'll talk about this concept of calibration, and more specifically, how you evaluate ML models or ML classifiers for their calibration. So just to start off with what the idea of calibration means, we'll start with this, a similar example as I discussed before, where a classifier is trying to predict friendly trucks versus enemy tanks. And in a deployed scenario, a new image or a new instance comes into the classifier, and the most common output from, say, for modern neural networks that are commonly tasked to do these types of tasks is some idea of predicted confidence over each class. And so in this case, it's expressed as a probability. So say 0.6 probability that they think that this input is a friendly truck versus enemy tank. And the question is, how do we understand these values? Classifier calibration poses this, or answers this question by saying that these values are backed by the frequency of class labels. And what does this mean? This means for a classifier to be perfectly calibrated, for all possible inputs, the class for which the classifier outputs 0.6 and 0.4, 60% of the time the input should be a friendly truck, and 40% of the time the inputs should be an enemy tank. And so what this actually backs these values with is this idea of historic empirical frequency of the actual classes over the domain of instances or images in this case. So given this particular definition of classifier calibration, we not only can understand these values that are coming out of these classifiers in a particular way, but we can also evaluate our models according to this definition of calibration. And so this has gotten a recent attention within the ML community or the machine learning community due to the fact that there's observations about the deficiencies of modern neural networks for their calibration. But most of these works actually focus on this particular metric for evaluation called top 1 expected calibration error. And there's a lot that goes into this metric, and a lot of the metrics we'll be talking about today. But the point here is that we want to highlight one particular characteristic of top 1 expected calibration error, for which potentially can cause issues within particular mission contexts. And so, as an example here, now we're predicting this classifier is tasked to predict not just 2 classes, but 4, ranging from friendly tank to friendly truck to enemy tank to enemy truck here. The model will then output 4 probabilities. In this particular instance, the most probable class is this friendly tank at 0.6. And so according to this top one expected calibration error metric, this is what this model is being evaluated for. It's saying a perfectly calibrated model under this top one expected calibration error is that for all inputs for which the classifier outputs 0.6 as the most confident class, or the highest value that it outputs, 60% of the time, those inputs should be that class. So it's basically reflecting this idea of making a prediction of the highest confidence class, and the confidence associated that should be calibrated. Now, that's great if you're only going to consider the most confident class, but consider the following scenario. You have two classifiers. Both of them have the same most confident class here, but the rest of the probabilities output by the models are different. Now, according to top one expected calibration error, these two classifiers are considered the same. However, when you look at the other probabilities, these can mean very different things within mission context. Specifically, the second classifier, the one below the top one, the class of enemy tank actually has a probability of 0.4, which is very different potentially to an analyst than saying the top model saying there's only a 5% chance of enemy tank. So it's important to recognize the fact that this particular metric that's most commonly used within the machine learning community to evaluate their model calibration actually doesn't reflect certain mission contexts that are important for the practical usage of these models and the usage of their confidence. So this work, which is representative, which some of the work I'll talk about today is represented in this work we have that's currently under review, we're focusing on this idea of developing metrics for calibration that are more closely match certain contexts in which models are deployed, these classifiers are deployed. So we take a particular statistical framing of expected calibration error and create a larger framework over this, as well as develop specific metrics in that framework and highlight how they can be used. And so these consider a couple factors, namely application-specific trade-offs, such as we want to see how it's not just the calibration between particular classes, but between the idea of groupings of friendly vehicles versus enemy vehicles. See how the calibration reflected across those particular groupings. Things of specific instances of interest. So if we want to evaluate just for instances for which the ground truth real label is enemy vehicle, we can isolate those instances within our metrics to see specifically how our model is calibrated on enemy vehicles. And the last two I'm going to talk about with some examples from our paper here. But the first one is this idea of either focusing on the most confident class versus the full probability distribution. There's a whole gamut of considering the probability distribution in different ways that's sort of in between these two. And so we ran an experiment where we wanted to evaluate the current state of the art in classifier calibration according to these more context-focused metrics and observe how they perform compared to the traditional ways of evaluating expected calibration error. And so in our first experiment, we developed this metric that's called top K expected calibration error. And the base setup is this. We train a residual neural network classifier that's 50 layers deep. This is a very common architecture used for this task. And we train this model on a data set called ImageNet, which is a standard image classification benchmark used within the machine learning and computer vision community, which is to classify these images as one of 1,000 different classes. And we wanted to see, again, how these methods, these calibration techniques, compare to the baseline with respect to not only the traditional ECE, but also these other context-focused metrics. And so there's a lot going on this graph right here, but to break it down just really quickly, on the x-axis here, what you're seeing is groups of bar charts that were reflective of the base classifier. So this is just the ResNet 50 trained on ImageNet with no explicit calibration being performed, versus each of the other groups represent a particular calibration technique being applied. And on the y-axis, the bars represent the expected calibration error. So you're more calibrated for a lower bar. And on the key denotes the particular metric being used. And so if you just take a look at the blue bar here, what you see is according to the traditional top one expected calibration error, that all of these interventions with exception of focal loss actually do indeed reduce the traditional ECE. So this is just as advertised, and this is representative of the work that's currently out there. But if you consider more of the probability distribution, not just the most confident class, but say the top 5, well, you see the story is actually very different. And so this particular scenario where you're showing the top 5 could reflect the case where instead of showing an analyst just the most confidence class, you're showing it the 5 most confident classes. So providing them more information to make decisions. And in this case, the gap between the base model where there's no explicit calibration being performed versus these techniques that are trying to calibrate the model is either lower, they're closer together, or in the case of label smoothing, denoted LS here, is actually higher expected calibration error in these cases. And in the case where you consider the full probability distribution, again, it actually increases by quite a bit more. So the model, the interventions, or these calibration techniques either increase expected calibration error over the full output of the models, or perform about the same. And the point here to understand is that the top one, or traditional expected calibration error, is a particular view and assumes a particular usage of these classifiers. While if you look at more of the probability distribution, some of these calibration techniques that are explicitly reducing traditional ECE are indeed doing that at a cost at other different views of calibration, such as the top 5, or calibrating over the full probability of all classes. And so for the other experiment I wanted to show today, we wanted to show something that mapped to a particular use case. So a scenario in which you can use confidence in a realistic setting. And so what we chose to do is highlight this particular metric that we're calling inter-interval ECE. And to do this, we trained, again, that residual network, the 50-layer residual network, on this data set that is chest x-rays of patients that are going into hospitals that either have COVID or not. So the classification task is to classify whether this chest x-ray came from a COVID patient or not. And so you can imagine a scenario where such an automated system could facilitate the diagnosis for a clinician of COVID. But in this case, we're going to make the assumption here that the confidence values that are expressed in these predictions are not just the exact values of confidence that are produced by the model, but instead are organized in categories ranging from very low confidence to very high confidence. And what this means for the model is if you have, say, a confidence output of between 0.0 and 0.2, this corresponds to a very low confidence category. And so instead of the exact values, a clinician would see from the model very low confidence. This is very common within the human factors community because humans tend to understand these categorical notions of these continual values more than specific values such as 0.5, 4, 3, 6, 7, right? That's much more difficult for a human to understand than something like low confidence. Anyway, the point here is we want to see how to evaluate this model with this particular assumption on the context in which the model is going to be used. So here's the same diagram I showed before, except for now the bars represent the traditional expected calibration error, again, for this COVID CRX2 data set, and then as well as these interval-specific ECEs. And so if you focus again on just the traditional ECE, you can evaluate your model with, again, that particular assumption on interpretation of the outputs of the model. And we see here, roughly speaking, most of the models behave roughly the same, some slightly better than the baseline. But if you look at these more specific interval-specific expected calibration measures, you can actually see much more insight into the model. So if we focus just on focal loss here for a second, what we see here is the green through the blue bars, so the second, third, fourth, and fifth bars here from left to right, we see that there's errors that measure specifically the error of a model if it produces a value that is supposed to be in the low confidence region, say for instance for the green bar there, that is actually the degree in which it violates that assumption of being into that confidence category. And what we see here is that the model is actually very good at producing values that are representative of low confidence or high confidence in COVID. But in the middle here, where potentially the more confusing cases that a clinician may need to have the model express this uncertainty for, is actually the model is more poorly calibrated. And so this provides a specific insight into this particular this calibration technique that traditional ECE simply cannot provide. And that's sort of the point here that I wanted to show in this experiment, in that by using this framing of expected calibration that we produce, you can actually have metrics that reflect classifier usage, and so that you can better evaluate your model for how it will actually be used. Yeah, so this is, like I said, this is work that's been produced that's currently under review with support of many of the awesome people at the SEI on the team, depicted here in the top row as well. I didn't get to talk much about our work with our academic collaborators, R.T. Singh or Zach Lipton, but that's definitely part of the work, and we're super stoked to work with them. And if anybody has questions about that work, we can talk about it. But just to wrap things up, the
the point here is that machine learning models are able to express their uncertainty in their predictions, and that can lead to more informative, robust AI systems, specifically through allowing humans to reason about this uncertainty to understand when the model is likely to be incorrect in its predictions. And also, by incorporating this uncertainty in a larger AI system to take different actions based on model confidence, potentially resulting in more robust AI systems. As a larger view of this project, we're trying to evaluate models for their uncertainty, characterize that uncertainty, articulate that uncertainty, and rectify that uncertainty in models. And again, if there's any questions at the end of the talk, we can certainly discuss those particular parts of the project. But what's going to be next that we're going to focus on is, one, develop a demonstration highlighting the utility of these models expressing this uncertainty, and sort of a more tangible application that's more focused on a particular application that highlights this utility. And this actually involves this idea of articulating uncertainty in a way that a human can understand, as well as, our model certainly needs to be able to express it, and we want to evaluate our model for its ability to do that. So that's something that's on the horizon that you guys can look out for. But also, we didn't talk a lot about sort of this idea of characterizing uncertainty. In some sense, there's different sources of uncertainty in ML models. So there's different reasons why models can be uncertain. So characterizing that uncertainty so you'll be able to more accurately quantify it, but also be able to rectify it within your model is super important and something we're going to be working on coming up here. And the last thing I want to mention is, while we have some collaboratives throughout the DoD and actually in academia and elsewhere, we're always looking for more real-world use cases of this work. And so if you have a mission need for machine learning models that express uncertainty, definitely give me a call. We're always interested to hear about mission applications. And so my email's there depicted at the bottom. Feel free to drop me a note. Thank you.
We are now with Dr. Eric Heim for the question and answer session for Knowing When You Don't Know. Welcome, Eric.
Thank you for having me.
So we have a few questions coming in. The first one is, you talk about quantifying uncertainty, but what are some of the causes of uncertainty in ML models?
Yeah, sure. So I think the best way to talk about the potential causes of uncertainty when machine learning models are trying to make predictions is to talk it through the lens of what are the inputs to the model. So this is the form typically of data. And so you can think about it in terms of the difference between what you've trained your model on, that data, versus what you're seeing during deployment. And so for instance, so if your model is biased in a particular way towards a data set, so if you trained on tanks that are of a particular color and trucks that are of a different color, say black tanks versus green trucks, but you see something like a green tank, right, that's during deployment. In that case, your model may be confused about what that object is simply because it has characteristics of both classes. And that represents a bias in your data set. Similarly, there's things such as changes in how you process data during deployment versus during how you process your data during train. There's rare events, so things that are just very, very uncommon, but actually do happen when deployment. This can be a cause of uncertainty in your model. But note that all of these things can be actually rectified, but simply having more data to actually train your model on. And so that represents one potential challenge or one source of uncertainty. But another one is simply challenging cases. So if the data coming in is particularly noisy, such in the visual domain, such as blurred images, that's just something that's inherently difficult for any machine learning system to deal with. Or things that sort of look like multiple different classes. So if I had a tank that looked like a truck, in that particular case, that borders the line between those two classes, which are just inherently difficult to classify. So that can be cause of uncertainty. So there's a number of ways that a machine learning model can become uncertain. And these are all ways that you need to somehow rectify, or at least be able to understand, quantify, and handle some way within the machine learning model.
We received another question. This one is asking, we need a system that will be able to identify a T72, for example, with a 90% or better confidence level. How does this work assist in that goal?
Yeah, so this is an interesting question. When you say 90% confidence level, sometimes what you mean here is 90% accurate. So every time it sees a T72, 90% of the time it's able to identify. That's typically a metric associated with accuracy. Now, what you kind of want in the confidence end of this is that you want your classifier to be express confidence in these predictions that are alongside of the predictions themselves. So when a model says it's 90% confident in this prediction, what you should sort of understand behind that confidence is something like you would expect that out of every time your model says 90% confidence for a T72, it is going to be right 90% of the time, which is different than being right. It's predicting how likely it's going to be correct versus how often it is correct. And so the process of saying I want my classifier to be 90% confident is related to the idea of being 90% accurate. But the former really focuses on the idea of the model being able to quantify how likely it is to be correct.
Mm-hmm. Thank you. There's another question coming in. While uncertainty can inform downstream processing, as you discussed, there are some cases where you simply want your model to be certain. Once you've identified these cases, how do you rectify uncertainty?
Yeah, so this is actually a really good question. So obviously uncertainty in certain cases is simply unacceptable, right? And so if you've identified a case where your model is uncertain for which you really, really want it to be certain, there's a number of things you can do. But really what it boils down to is try to characterize the source of uncertainty in your model and sort of why your model is uncertain in that particular instance and correct it in the model in some particular way. So for instance, if you see your model is particularly poor at images being just given to it at nighttime or in a different context, simply because your model doesn't have a lot of instances of, say, of the deployment environment under that particular context, which is nighttime in this case, right? And so if your model is consistently uncertain in those cases, and you want to deploy your model in that context, what you have to do in that case is likely get a bunch of instances that you want that are in that context and retrain your model. Now, the important thing about uncertainty here is that if your model is able to accurately express uncertainty in those cases, this can lead to identifying those particular failure modes. So I think it's important to, in this particular case, identify the cause of uncertainty and then use that to guide your rectification procedures, such as collecting more data and retraining.
The cause of uncertainty. We have one more question coming in. We'll see if we get any more, but is calibration the only way to assess the quality of confidence measurements in ML models?
Another good question. The answer is no. So as I talked about in the talk, calibration sort of reflects this idea of predictive uncertainty. So it's backed by this idea of what you should expect in terms of how the likelihood of a model being correct. But there's a lot of other types of uncertainty, such as, like I talked about the sources of uncertainty before. Some of those can influence predictive uncertainty, but in and of themselves are separate from it. For instance, you can think about uncertainty in the model's parameters. So if I learn a model and it adjusts its parameters through some optimization procedure to arrive at some model that is the solution given my training set, and I've given some new instances, my model can make pretty uncertain predictions simply because the parameters of my model are not necessarily, my model is not necessarily certain its parameters. What this typically means is that the whatever instances I'm seeing are simply different than the ones I've seen before in some way, right? And so this can express that this is not necessarily a noise thing. This is not necessarily a really difficult case thing, but this is actually a source of uncertainty that is simply caused by instances I haven't seen before. And conversely, if you remove that idea of uncertainty with just instances I haven't seen before, from this idea of predictive uncertainty, the other component of that is uncertainty that's just, you can't eliminate with new training data, like I've discussed before. So those two separate ideas are useful. And there's also another way of interpreting or learning models that include ideas of not just making these point predictions over classes, but have ideas of mean predictions and variance of predictions. And those things tell you different things as well. And so if you view the models in those particular ways, you can, opens up to a whole new slew of metrics and a way of quantifying uncertainty. And of course, I just talked about classification problems in the talk, but if you consider more sophisticated problems, certainly they have their own ideas of uncertainty and interpreting for those particular problems. So like, for instance, object detection, which includes both classifying an object and identifying its location in an image. Those two components can contribute to uncertainty, which is going to be different than just calibration.
I believe we have time for just one more question. The question is, analysts and users usually don't know how a model was trained, so they won't know when a model is confident, but shouldn't be. How does this work help with that problem?
Yeah, so the idea of having these metrics, like the ones I've talked about, directly addresses this point. So if you look at the output of your model, right, it makes a predictions. You don't have to know anything else about the model. And it makes a prediction and an associated confidence estimate, right? And this confidence should mean something to an analyst, and they don't need to know anything about how the model was trained to sort of understand the idea of confidence in a prediction. Now, the metrics here that we're developing are to ensure that that confidence actually reflects reality. So if I'm 90% confident, I'm right 90% of the time. So this work ensures that when a machine learning model outputs some confidence measure, it actually reflects that reality, as opposed to potentially other solutions that may learn a model that for that confidence is not well calibrated or does not have that good an interpretation that people can use.
Mm-hmm. Well, unfortunately, this is the end of our Q&A. We have to go, but thank you so much for your time, Eric. And to those who are tuning in, we're having a lunch break for 30 minutes. So please join us after the break at 1:30 p.m. Take care.
My name is Grace Lewis, and I am the Principal Investigator for the Predicting Inference Degradation in Production Machine Learning Systems project. If you've worked with machine learning production systems, you're likely familiar with inference degradation, which is loss of predictive quality in machine learning models over time due to differences between characteristics of training and production data. Current industry practices evade inference degradation by doing periodic retraining and model redeployment strategies, rather than monitoring for it. These strategies become less feasible as DoD AI systems move into the operational AI space, characterized by fast tempo and limited resources. Unfortunately, timely, reliable identification of inference degradation is difficult. Our solution is to develop a set of empirically validated metrics that predict when a model's inference quality will degrade due to different types of data drift. In the process, we develop a test harness that will help model developers define drift detection metrics and thresholds for their models so that these can be integrated into MLOps pipelines and monitoring infrastructures, therefore effectively detecting inference degradation in production machine learning systems. We anticipate that users of our test harness and drift detection metrics will have better information to detect inference degradation in deployed models and therefore prevent misinformed decisions, costly reengineering, and potential system decommission. If you want to hear more about our work, come to our presentation on day 3 of the research review. Talk to you soon.
The heart of the SEI is research. And our predominant objective is to help software practitioners learn SEI technologies, to help them in their work and to enhance software capability that's affordable, timely, and reliable.
Some of the innovations that we came up with in terms of acquisition with the rest of the community are now new acquisition paradigms for the Department of Defense. And that goes all the way down to the cyber operators. We have great innovation in terms of how to do exercises and actually train our cyber operators for their day-to-day work. And our innovation gets used every day in that perspective as well.
When an innovation leads to something useful, it's the socio-technical knowledge and skills that allow us to successfully insert those innovations into programs, into the world.
And so the challenge at the SEI is to make sure that those innovations, even if they're not sexy, that they get enough attention paid, not just to the research itself, but also to getting it transitioned in the right way.
Everything changes when an innovation is adopted, right? I mean, some innovations become a ubiquitous part of everyday life, and some are just incredibly important for certain groups of people. But adoption means change. That's what it is at its core. And so I'm always excited by opportunities to escort an innovation from a small group of early adopters to a larger user population, and ultimately seeing that how that innovation lives and plays, because there's always a ripple effect. So seeing an innovation take root and become part of people's work is really rewarding.
your system has an architecture, whether you know it or not. I think that could very well be reflected in technical debt as well. Your system will have technical debt, whether you're aware of it or not, because if you're dealing with a successful, long-lived system, you're dealing with change, you're dealing with technology upgrades, you're dealing with developer turnover, you're dealing with software architects who might have or may not have the right skills based on the time of the development. So I think that's how they really relate very well together in design trade-off analysis.
I prepped it actually. That's a good one, because I know it's going to come up with the continuous integration. So we have been doing the integration of maybe years, like even though when I wrote the program from 30 years ago, I was in integration. But what the continuous integration means, that's a little bit going to come back to this graph shortly. So we have our various team members, like the team A, team B, team C are building the code, and within their environment, eventually we have to merge this code, and then we have to build that. What build means, like we're just getting a code and then creating a binary artifact. So this binary artifacts, it's going to be used in the production or the testing environment, right? So this is kind of like a build process. We have to understand what the build means. Beta is going to get the code and then package it, and depends on the build steps and creating some binary artifacts so we can use for various things. So now in the concept of the DevOps or the modern thinking, we are adding a continuous term here. We are adding a C term. Like this is kind of like an integration level. Now suddenly we are adding a continuous integration. What the continuous integration means, so we're going to get a code. We will get the code from repositories. Remember we mentioned about infrastructure at the beginning. So we will get the code plus other artifacts. Other artifacts is infrastructure code. Other artifacts, how we're configuring system. Now build that. Now we are building, so creating an artifacts, creating and the testing, and then eventually we're going to do the deployment shortly. So continuous integration will help us to gather any changes from repositories. We get from repositories that kind of get change happen in the repos, and developer pushed it. A team pushed something and B team for the person wise or a team. So we can grab the code from repository and package it, and then make sure delivering to the staging testing environment. So in the build process, we're not again just getting a code, we are getting other artifacts, because the software that we are building right now, there are so much dependencies in the software. That goes back to the SPAM question at the beginning. So we get the code, we get other artifacts, how we are creating a deployment as an example. How are we creating a dependent libraries as another package? And so we get all together. Maybe we're building the code, we're just going to push into production. We don't know what operating system requirements are behind it. And third one is, this is the first time probably you may be hearing that, write the code, we have the infrastructure, now we're adding a documentation in it. So don't think about that we are creating a Word documents in the context. This is more about specific information about our system. Our system that we are building, maybe some specific user guide that we are creating. Maybe we have some notes that it is relevant to how we are configuring an environment. Maybe some notes that's specific to how we are writing the requirements for the code that we are building. So suddenly build is combination of the code, artifacts, and other documentation, we can build it. Because as a result of the build, we are creating a artifacts. So artifacts is a binary, but sometimes binary is not enough to run with the production environment, because you need other information for a security perspective, for a maintenance perspective. I saw so many examples and the bad practices in software engineering thinking. we are running in the build in the production environment, we're never able to go back and reproduce again because we don't have right build steps, right configuration, right documentation, right infrastructure code pieces in place. So the continuous integration is basically combining all of them. So let's look at the continuous delivery and deployment. Let me get bigger here. So I'm just going to give a quick example about the just to set the stage SDLC. So we have the requirements that we write it, and we have the design, kind of like architect as well here. And we have a development and we have a testing. So we are in the deploy. That goes in the production environment. So typically continuous integration is happening somewhere here as a continuous integration. So we got the code, we are building. Now we make sure that we have the CI. So continuous integration is going to get a build artifacts for us. What is next? So after build artifacts, there are two concepts. One is a continuous delivery. Another one is deployment. It's often a confused term. So both of them intend to really go into the production environment. So deployment, get artifacts and do some testing or requirement testing, including security, and automatically pushed into the production environment. That's kind of deployment goes into the production, which user can see as live as an output as a result of the build. What the continuous delivery is, it is manual to production environment, but it is automated into the staging environment. So as an organization, we need once we build artifacts, we can go to test harnesses. We can initiate the different test harnesses. We can create more test cases, test environment. We can deliver the artifacts into the staging or test harnesses, so we can do more testing for the artifact that we build. When we are done, we can manually put this artifacts into the production environment. That's a continuous delivery, and deployment goes automatically. So next question we may think about that, can everybody do continuous deployment? It depends on the business needs. It depends on the system that we are building. Can everybody continuous delivery? Yes, we should do continuous delivery because that's the intent of the building a software. First, we can test more and more and more. When you're ready, you can manually get artifacts if you want to put into your production environment. Okay. So quick summary, continuous integration will help us to build artifacts from code, infrastructure, documentation, all information. We can package it, version it. Then we can test it, the content in the staging environment. Make sure everything is working fine, which is delivery. And when we are moving into the production as the users that can see automatically, that's a continuous deployment. So deployment really is specific to the business need. Deployment is specific to organization needs, that is an example.
Bringing all those people together from different places and different ideas really helps us form perspective, but it also helps us then spawn innovation across the community, right? We kind of become the seed or the germ of the innovation, and working with people over time, right? Whole industries are born.
We get great new ideas when we try to work across divisions. I think we get great new innovative ideas when we work with members of the software engineering communities and through our professional societies.
We have a collection of incredibly talented folks in their respective fields, and it's not just the researchers, as great as they are. It's the folks that do all the things that enable the researchers to do their jobs. We have some of the best and brightest in the various disciplines we all serve.
I support SEI staff by providing information that they need. I mean, we're not doing the technical work, but we're trying to understand it to the point where we can provide the resources for the technical staff to do their work. We learn a lot about the terminology, and it makes us better when we're developing search strategies.
knowing that we have an SEI family that is made up of people from diverse backgrounds, educational backgrounds, cultural backgrounds, I think brings a lot to the table when you're tackling really hard problems for our sponsor.
Good ideas come from really bright people. And interestingly, one of the things that inspires me and keeps me focused on the work of the SEI is all of the really smart people we have here.
Enterprise cybersecurity data, whether it's on your systems or in transit, is bigger and more varied than ever before. I hope you'll join us at FlowCon 2022 this coming January from the 11th to the 13th to see our presenters share new techniques and best practices for identifying diamond-in-the-rough insights, share their experience building machine learning models in a principled and methodologically sound way to support cybersecurity. You'll see talks that introduce novel situational awareness perspectives to observe attacker behavior, secure sensitive data, and manage risk in cloud deployments and on-prem. We all know network and system process artifacts can be far too many to store and analyze all in whole. Sometimes they're obfuscated by encryption. But our speakers from academia, industry, and government will share with you their research in contextualizing data and building scalable analytics and metrics to help you use your data to defend.
A lot of the legacy code that's out there, nobody's going to start analyzing that code and looking for vulnerabilities or defects in the source code. And so this might be a way...
Except the bad guys.
Except the bad guys. Yes, exactly. If they can get their hands on the source code, or they might be attacking it, through
fuzzing it or something else,
fuzzing and other dynamic analysis techniques. But the idea is that without much manual interaction at all, we might be able to remove a whole class or multiple classes of vulnerabilities in legacy code without using manual labor to
completely
do that.
Automatically.
That is the goal.
So in these techniques, in these ways, I think about the data that the DoD is collecting, and particularly in a cybersecurity context, in terms of what it contains and what we can mine out of it, what we can identify, and how we can build intelligence. And so one of the ways that we do that is through information extraction techniques. So broadly, information extraction is the process of taking a set of, typically we think of them as documents, but it could be any data set, and identifying the pieces of information that are distinguishing and important for gaining knowledge and insight into that data set.
Many times people go out and buy point solutions, but they don't understand how we got there. And technology of itself you just can't place technology in an organization. There are a lot of other factors that are involved, to include a culture change. So collaboration to me is being tightly coupled with our mission partners.
A benefit that we've had in our causal research of having a CMU staff or researcher participate is that our CMU collaborator who was applying causal search to cancer research data sets cut the roadmap in researching that cancer by like 6 years. The same technique was then shared with us to apply for use for our Air Force customer. So that's been really cool to see that research in a complete different domain within like 1 year made it over into our area, and we've learned from that. And that's now a standard approach for what we call feature engineering that we're doing.
I don't think people realize or appreciate how vital SEI research and expertise is to advancing national security in general and customer capability specifically. There have been numerous occasions during customer feedback sessions, for example, where customers have told me and a colleague of mine verbatim that we would not have been successful without the SEI.
I think SEI plays the role of catalyzing the software engineering community, bringing different parts of the DoD, bringing industry, bringing tech organizations together. When we can bring all these organizations together and work with us on some of the key challenges, it really opens up ideas and perspectives.
a technology standpoint, it is very different than it was 5 years ago, or even 1 year ago, honestly. The telecommunications and telepresence technology that exists out there has sort of been supercharged and obviously highly motivated by what's been going on over the last several months. From a network security standpoint, another aspect that's transformative over the last 5 years has also been an explosion in the number of devices that exist on home networks. So now you have all these IoT devices. People often will buy and install something that has a network connection that'll phone out into the internet and not even know that they did it.
Welcome back. Next up is Dr. Grace Lewis. Dr. Grace Lewis is a principal researcher and the lead of the Tactical and AI-Enabled Systems Initiative at the Carnegie Mellon Software Engineering Institute. She's currently focused on 2 projects in the growing field of software engineering for machine learning systems, characterizing and detecting mismatch in ML-enabled systems, and the predicting inference degradation in production machine learning systems. Her current areas of expertise and interest include software engineering for AI and ML systems, software architecture, edge computing, and software engineering in society. Today, Dr. Lewis will speak on predicting inference degradation in production machine learning systems. Those that have worked with machine learning production systems are likely familiar with inference degradation, which is the loss of predictive quality in machine learning models over time due to differences between characteristics of training and production data. Today, Dr. Lewis will discuss how to develop empirically validated metrics that predict when inference quality will degrade due to the different types of data drift. Please welcome Dr. Lewis.
Hello, my name is Grace Lewis, and I am a principal researcher at the Software Engineering Institute. Today, I'm going to talk about our FY21 Lens project titled Predicting Inference Degradation in Production Machine Learning Systems. The motivation for this work is that the quality of the inference of machine learning models after they are deployed changes over time, mainly due to the differences between the characteristics of the data that the model was trained with and the data that that model is encountering in production. The state of the practice in industry to deal with inference degradation is to do periodic retraining and model redeployment. So in a way, what they're doing is evading inference degradation as opposed to monitoring for it. However, this strategy of periodic retraining and redeployment becomes more infeasible as DoD AI systems move into the operational AI space, which is characterized by scarce resources, fast tempo, and significant implications of failure. The problem with inference degradation is that it's really difficult to detect in a timely and reliable manner. If you look at the diagram on the left, if you do it too frequently, if you retrain before the model has reached its threshold for inference quality, what you're doing is you're wasting resources training and deploying that retrained model when it was not really necessary to do so, in addition to normal redeployment risks. If you do it too late, then what happens is that you're basically operating with a model that is not really operating at optimal conditions. And so, for example, if you're using a machine learning model to do object detection, there could be some objects that you miss because you retrained too late. In addition to that, as shown in the diagram on the right, not all degradation is gradual. Sometimes it's just sudden. Imagine a situation where, again, you're doing object recognition and some kind of disaster happens. In that case, you really have to redeploy quickly because you're going to be operating in non-optimal conditions for a really, really long time. So basically, the failure to recognize inference degradation in a timely manner can really lead to misinformed decisions, costly re-engineering, and potential system decommission for DoD systems because basically the users stop using it because they don't trust it. So as a solution to this problem, this project basically has two goals. The first goal is to develop a set of empirically validated metrics that can predict when a model's inference quality is going to degrade due to different types of data drift and therefore requires retraining. The second is to develop a test harness to help model developers really understand how their models are behaving due to drift and then select appropriate metrics and thresholds for monitoring. So the advantage of doing this is that the developed metrics and their thresholds can be integrated into MLOps pipelines or any type of ML model monitoring infrastructure to basically determine two things. When a model really needs to be retrained, and second, what are those thresholds that you need to be looking for that minimize the time that that model is not operating adequately? So in order to do this, we set up a series of experiments. The first thing we did is that we selected the SAR dataset as the dataset for experimentation, which we classified as a DoD relevant dataset because it's pretty close to the image classification datasets and data types that are used by DoD ISR applications. This is a dataset from a Kaggle competition where the goal of that competition was to basically identify icebergs in satellite images. The second thing is that based on this SAR dataset, we identified relevant drift types that we could introduce into this dataset for experimentation. The drift had to be of sufficient magnitude to be detected, but it also had to be realistic. And this proved to be one of the most challenging parts of the project because there is not a lot of work out there in introducing realistic drift into datasets. And then, as a third part of the experiment, we now had to identify candidate metrics that would be able to identify each type of introduced drift. And for doing this, we performed quite an extensive literature review of drift detection methods to understand the state of the research and practice and be able to identify metrics that would be applicable to the type of drift that we introduced in the data sets. So as far as experiment set and metrics, we created a set of actually total of 16 experiments where what we did was, based on the SAR data set, we identified real scenarios that would indicate that drift is occurring. So for example, if the number of icebergs declines with seasons, this would be an example of gradual drift. If there is a reoccurring decrease in icebergs over multiple seasons, this would be an example of reoccurring gradual drift, and so forth. So what we did is we identified 16 experiments based on these scenarios and these drift types, and by using different rates of drift, we were able to come up with 16 separate and explicit experiments. As far as metrics, we decided to work with basically 6 metrics, 4 distance metrics and 2 error metrics. So the distance metrics are important because basically what they do is that they measure the difference between 2 probability density functions. And error metrics, basically what they do is they compute a statistic that has a well-defined distribution that corresponds to the null hypothesis. And by having 2 types of metrics, we're basically looking at drift from 2 different perspectives or assumptions. Our test harness that was developed as part of this project is composed of 3 tools. The first tool is the trainer, and that trainer, it takes in a base data set, it takes in the configuration file, the model portion, and it trains a CNN-based model with a given set of parameters based on TensorFlow. The second tool, which is the drifter, it takes as input the base data set, and it takes also as input the same experiment configuration file, but the drift section. And then basically what it does is it generates a drifted data set from this base data set and based on the drift that we're asked to introduce into the base data set. And then the third tool, which is probably the most important piece of the project, is the predictor tool. The predictor tool takes as input the base data set, the drifted data set, and the trained model. And in addition, the same configuration file, but there is a metric section. And then what it does is that it runs the trained model with the drifted data set and produces 2 things. It produces prediction results. What were the prediction results based on that drift data set? And also, what were the values of the prediction metrics when we did this over time? The tool supports 2 different workflows, which we believe is very important for engineering these types of systems. First of all, it supports a model development workflow as follows. The trainer component, you can use it to train the model, or you can use whatever framework or tools you're comfortable with, but the first part is to train the model. Then what you do as a model developer is you define drift induction functions for those type of drift that you believe are relevant to the scenarios that your model is going to encounter in production. You run the drifter to produce the drifted data sets. Then you would run the predictor to obtain measures for the defined drift metrics, and you basically would iterate over and over, doing some analysis until you can say, well, two things. Here is a trained model, but in addition to that, here are the drift metrics that I would like to have monitored in production along with their thresholds to be able to detect at runtime in production when the model is drifting. As far as the model integration, deployment, and operations workflow, basically that workflow, it starts with the trained model and that same set of drift metrics and thresholds. And in this workflow, you would wrap the model into a machine learning component if needed. You would set up model monitoring using the same predictor tool from the first workflow as part of your infrastructure to monitor specifically for those drift metrics and thresholds. Then you would deploy the model, and then what happens over time, the predictor would be running, at some point, the predictor and its infrastructure would notify the system that drift is happening. And at that point, based on how the system was configured, it could either generate an alert that says, oh, the model is drifting, something has to be done, or maybe we have some type of automation in place where basically what it does is it retriggers some automated model retraining or model replacement process. Or in maybe a more sophisticated scenario, you could take the data that is being produced by the predictor tool and do some additional data analysis, like for example, to detect false positives or something along those lines. One thing that we set out from the start, from this test harness, is that we wanted it to be extensible and flexible because we want to make it available to the open source community, to developers, to practitioners, so that they can study drift in their models. So the architecture of the test harness includes very explicit and very well documented extension points. So you can introduce new data sets, new drift induction functions, and also drift detection metrics. And in addition to that, as I highlighted in the previous slide, experiments are defined via configuration files, and support different types of drift analysis. Like for example, you could use it, as in the previous workflow, for defining what are relevant drift metrics and thresholds for monitoring. You could also use it in a more experimental way, just to see how the model behaves when introducing new different data types, different drift types. And also, you could also use it to decide, like, what is the threshold at which you think it's necessary to incur the cost of gathering new labeled data for retraining. So the test harness supports different extension points. It supports multiple configurations and also different types of analyses. So let's talk about how we decided to do drift induction in our system. Well, there are two options for modeling drift behavior. The first one would be to apply drift to the feature space and observe the drift independent of time. An example of this for object recognition would be to alter the actual images using, for example, blurring techniques or changing contrast or changing color. That would be applying drift to the feature space. Another way to introduce drift is to apply the drift to base rates and observe the drift by time series. An example of this would be to change the distribution of the input data and see how the model behaves with this change. What we decided to do is we selected the second option for several reasons. First of all, it was more compatible with the scenarios that we wanted to evaluate in the SAR dataset. And second, because we decided that it would be more applicable not only to different types of data, but also different types of models beyond CNN models. So what is the process that we followed for drift induction? So basically what we do is that in our samples, which is the drifted data set, we sort the samples into configured bins by their classification. So on the left is an example of what the configuration file would look like for the drift portion. So in our case, in the SAR data set for iceberg detection, you have two classes. You have images with no icebergs, which we call 0, and images with icebergs, which we call 1, and these are our two bins. After that, you would define how many time boxes do you want to analyze the data in. And so in this particular case, going back to the diagram on the left, what we have decided is that the data set has 9,999 samples. And basically what we said is we want 3 time boxes of the same size, which is the 3,333. And when you run the process, basically what it does is, based on the percentages by time box, it extracts samples from each one of these bins and creates the time box. So going back to the example on the right, this is a condition for this, or the example here is sudden drift. And basically what we're saying is, when you do the drift induction, for our three time boxes, we want the first time box to include 65% of icebergs, which is 1. We want the second time box to include 40% icebergs, and we want the last time box to include 60%. So that going from 65 to 40 would be an example of sudden drift, and that is how we induce drift into the data sets. The tool itself, basically then what it does is the user, the model developer, would call the drifter with a base data set and the experiment configuration details, which, as I showed before, include the drift type to introduce. The drift algorithm, which in previous case was sudden, is matched to the actual code that applies sudden drift. And finally, the data set with drift is created, and it's linked to the base data set, and it's ready to use by the predictor tool. So once again, the extension points basically allow us to not have to change anything in the code if you want to create new drift functions. What you would do is actually create a new drift function and link it to the tool. The predictor, what it does based on this information is now that it has a drifted data set, basically, first of all, it runs the trained model with the drifted data set and saves all the predictions into a prediction file. And then for each configured metric, it calculates that metric per each time box and saves it in a metric file. And once again, the extension point here, as is shown on the right, basically says, look, for the metrics that we want to run for this particular experiment are two metrics. We want to run KL divergence, and here are the parameters to do that. And we want to run the KS statistic. And once again, this is done in configuration files outside of the code, which allows for extensibility. So what were the results from our initial experiment run? So once we had the test harness ready, once we had the data set, we had the drift induction scenarios, everything ready, we did our first end-to-end run with the test harness. However, unfortunately, the results were not what we expected. Basically, what happened was that the model that we selected was not sensitive to the way that we induced drift. What we did is that we selected one of the models from the same Kaggle competition, and basically it's an object classification model. And so what we realized is that the type of drift that we were introducing is really more relevant to a time series models of counts of icebergs rather than a classification model to identify if an image contains an iceberg. So as you can see on the right, there is barely any difference between the baseline, which is the data set with no drift, and our most aggressive drift scenario. You can barely tell the difference between those two. So what happens is we had to repeat our experiments. And so basically the next step for us is to build a time series model that is fit to the aggregated output of the original classifier. However, because it does take time to set up the experiments, to create the new trainer, to change the configuration file to the types of drift and things we want to introduce, we wanted to make sure that our hypothesis that we would be able to observe drift was correct. So what we did is that we generated a simulated data set, and we added drift into this data set, and we selected a subset of the metrics, and we said, okay, would this work if we did that with the SAR data set? And the nice thing is that it does really work. The results with our simulated data experiments show that different metrics are able to capture different types of drift at different points in time. So looking on the right, this is the value of the metrics of four metrics that we selected for evaluation. The baseline is the green. The orange is an example of gradual drift. The blue-purple is an example of recurring drift, and then the pink is an example of sudden drift. As you can see from the Henninger distance metric, that metric doesn't detect the sudden drift at all. You can see that the pink is overlaid with the green. On the other hand, all the other ones are pretty good at detecting sudden drift, some better than others. And in some cases, like for example, for the TS statistic, it recognizes sudden drift very, very quickly. In addition to that, you can see that at least for KL divergence, KA statistic, and the T statistic, you're able to detect the different types of drift almost within 10 new samples. So the data from our simulated data experiments is showing promise. And so really the next steps for us are to repeat the set of experiments applying drift and creating the time series model and doing it with the SAR data set. So what are the project contributions? First of all, the easy to use, extensible, and flexible test harness software. Like I said before, it supports model development and the model deployment workflows. What it does, which is the great advantage, it provides input to MLOps pipelines to figure out what drift metrics to detect and monitor in production, as well as their thresholds. And also the extensibility really supports new data sets, drift induction functions, and drift detection metrics via extension points that do not require modifying the code of the test harness, but rather writing new algorithms for these functions and metrics if necessary. The second contribution is a set of validated metrics for detecting different types of drift. Once we finish running the experiments, we will have that set of validated metrics. The way we introduce drift induction functions, those are also going to be shared as part of this project, and they can be applied to other data sets, not just the SAR data set. And in addition, the summary of the state-of-the-art drift detection methods that we had to do as part of identifying metrics. So the next steps for us, first of all, to conduct additional experiments with this new time series model. Second, we're going to document and publish results in both a software engineering and a machine learning venue, because that way we get to both types of audiences. And third of all, we're going to release the test harness as open source by the end of December 2021. And by doing this, what we're looking for is to collect feedback from all of you. We want to collect feedback on DoD relevant scenarios, on drift types that you're seeing in production, and also applications of how you would be using this tool as part of your model development and deployment and operations process. This is the team, and with that, I am very happy to take questions. Thank you.
We are now with Dr. Grace Lewis and her team for the question and answer session for predicting inference degradation in production ML systems. Welcome to the live session, everyone. So we have a few questions coming in. It looks like the first one is, what was the rationale and advantage for applying drift to base rates instead of feature space?
Okay. Thank you. That's a good question. And I also want to take the opportunity to introduce my two colleagues that are here with me today. Sebastián Echeverría, the lead person on the tool development portion of the project, and Dr. Jeff Kravitz, who is leading the experimentation effort. To answer your question, so when we talked, during the talk, we talked about two options for introducing drift, right? One was to apply drift to feature space, and the other one was to apply drift to base rates. Given the data set that we selected, which was the SAR data set for iceberg image detection, we decided on applying drift to base rates because it was more relevant to the type of drift that you would observe, let's say in practice when you were studying this data set. Iceberg, what would happen is that they would probably melt over time, or they could move over time or break apart. They would have seasonality. So definitely that was more representative of the drift that we would expect to see in that particular scenario. In addition to that, because this is a one-year project, we had to limit it in scope. So initially we'd said, okay, our scope is going to be models based on CNN for object detection. In doing this, we also expanded the scope of what we could apply our tool and our experimentation to. So that's why we decided to go this way.
Thank you. It looks like there's another follow-up question. This one is asking, I know that you have made progress since the video was recorded. Can you talk about the progress made and whether the simulation results are holding?
Yeah, okay, no, that's a good question as well. The short answer is yes, the numbers are holding. Also, one thing that we've done in this project is we've been very careful about giving equal priority to the experimentation and into the tool development, because we're really striving for extensibility of the tool. So I would say we've made progress in both sense, like in the numbers in the experimentation, but also tool development. Jeff, I would ask you to please answer the part about the experimentation and what you are seeing so far.
Sure. I think while we've given equal time to tool development and experimentation, a big thing that we noticed toward the end of the project is that we needed more tool development to happen before we could adequately experiment, right? And so since we've focused on that in the last couple of months, we've done some very initial exploration into rerunning the experiments while using a time series model to understand the expectation of the simulation over time, and use that as sort of a comparison for what the categorization model was seeing. But in implementing that, we've spent more time integrating that time series model, so our expectation about the future, into the test harness that we developed, in lieu of actually doing the experimentation yet. You can't really test it until you've built it.
Right.
Okay, we have one more question that just came in. Are there plans to continue this work?
Yes, I mean, definitely there are plans to continue this work. I mean, we've just started scratching the surface. We've only implemented one type of drift, as you saw. We would love to see we could extend the tool to also apply drift to feature space. In fact, we're working on a proposal that we hope gets funded to continue this work. We also want to basically, we want modeling drift behavior to become part of a workflow of people developing models, right? So I have my checklist. I check for this. I check for this. I check for that. Oh, let me figure out how my model is responding to drift. So definitely we have plans, I would say, highlighting two different things. Like I said, one is to be able to introduce more types of drift. The second is to be able to basically change not change, but influence the way that people develop models. And I would also think that we want to also extend the tool set with like providing more assistance to model developers, so that model developers also can make better choices about the type of drift that they want to introduce. So given that this is how I expect my data to drift when the model is operational, this is a type of drift I'm thinking about, and the tool would automatically introduce that drift into the data sets. Actually, that proposal is going to be led by Jeff. So once again, I'm going to pick on Jeff to talk a little bit about what he's thinking for the future.
I think that encapsulates it pretty well. There are really, data scientists tend to develop models, and there's a lot of QA that goes into model development prior to deployment, that we'd love to make sure you can make it easy for data scientists to use these tools, understand what's going on, and then have confidence when they get to deployment that they at least have thought about what's going to happen when the world inevitably changes. We'd also like to be able to link what the data scientists find in their drift exploration with what your DevOps and MLOps and engineers are going to do when they do monitoring for deployed models. So rather than just knowing, hey, like we're getting a series of bad detections, or we think drift has happened, now you've already pre-worked the scenario, and so it's these metrics that we're pinging on, and so we have some expectations about what we'll have to change or what we expect is going wrong. And obviously there are a number of consumers that happen sort of downstream or after the models perform inferences that we'd like to make sure that we can interface with, so that your analyst is looking at model output and needs to know what the quality of those inferences are. You have another system that's consuming those inferences and using them for some other aggregation or synthesis, and so that should have some automated method of understanding, hey, I can trust these right now, or maybe I can't, right? And so that serving those sort of three masters is what we're thinking about for follow-up work.
Right. And also, Sebastian, if you could please talk a little bit about some of the tool improvements that you would like to see going forward if you had more time.
Sure. So one of our goals when building the test harness that we're creating is that it should be flexible enough to support different use cases, so that it's not really a tool that we use just for this project, but it's something that can be used going forward by different groups of people. So we've made several parts here and there that can be configured, things like the type of treat that you want to support, and it's very easy to add things like specific metrics. But there are some of those parts of the tool that, even though they can be extended, it's not as easy or as fast as it could be to be extensible. So there's several pieces, like adding new types of data sets and so forth, that we could automate more, so that it's easier for people working with this to more quickly integrate the tool into their workflow. And also this tool can be used for both the when you are preparing a model and working with a model, and it can also be used later at a stage when you're in production in order to see how your models are working, and we focus mostly on the first part, on working with the model. So some other improvements that could be done on the tool would be to allow it to be more easily integrated into production, so it can be used to monitor how the model is behaving with the real drift.
Correct.
So is there anything in closing that hasn't been asked that you think the audience should know?
More than that, I think it's a request for, I would say, a request or a call for collaboration. Of course, no, the data set that we were working at, it's a public data set. Because it's open research and we want it to be as close to DoD relevant as possible. But if there are any organizations out there that have this concern about how to monitor drift in production, and would like to volunteer their data sets, or would like to work with us on validating with how generalizable both our method and our tools are, we would definitely welcome that collaboration. All our information is in the slides that we shared today. So thank you.
Thank you for your time. And this is just a reminder that if anyone wants to reach out to us outside of our QA sessions, please feel free to reach out to info@sei.cmu.edu. Thank you, everyone. Next, let's look toward the future. As you have heard over the last 2 days, software-enabled systems and applications will continue to play a critical role in every sector of our economy. Right now is the time to re-envision the future of software engineering. Architecting future software-intensive systems requires software engineering advances. The Carnegie Mellon University Software Engineering Institute recently completed a year-long study of the future of software engineering and creating a multi-year research and development vision that included roadmaps and thinking about next-generation software-reliant systems, called the National Agenda for Software Engineering Research and Development Study. Due to the abstract nature of software, it continues to grow within and without bounds in capability and complexity and interconnection. There seems to be no plateau in the advancement of software and therefore no end for challenges in software engineering. To make future software engineering systems safe and predictable and evolvable, the software engineering community must improve and provide sufficient investment from private and public sources. We must work together to advance the theory and practices of software engineering and be more strategic than the next generation of software-reliant systems. The Carnegie Mellon University Software Engineering Institute is leading the community in creating research and development vision in this area. Next up, we're going to hear from a panel that brings together research perspectives from CMU campus as well as SEI to talk about intersections between AI fusion and AI engineering. Throughout the panel, the conversation will cover what it takes to enable AI systems and how to optimize to enable transition and scaling of AI solutions. Please welcome Dr. Rachel Dzombak, Digital Transformation Lead within the SEI's AI division.
Hi, everyone. Welcome. My name is Rachel Dzombak, and I lead digital transformation efforts here at the SEI within our AI division. I'm really excited to moderate our panel today on AI fusion and AI engineering, enabling AI in complex environments. As we've been talking throughout the day, our researchers, our collaborators, they've all been discussing how AI offers leap ahead capabilities for meeting practical challenges, especially those in defense and national security. However, it's still really difficult to get AI right. And in our work at the AI division here at the SEI, we focus on trying to figure out what all needs to go into getting AI right. What are the engineering processes, the practices, and the frameworks that are needed to build AI the best it can be built? And so today, that's what we want to talk a little bit about. But as well, we're going to add into it this context on AI fusion. We're hoping to understand and look at the opportunities at the intersection of AI fusion and AI engineering, as both are critical to advancing the art of the possible in artificial intelligence today. I wanted to do some quick context setting before we get started. So AI fusion is a term to describe a vision for how all of the different parts of AI can come together in the future, with a focus on how do we get away from siloed capabilities, from looking at all of the different components in isolation. And researchers on campus and at the SEI are examining research thrusts in AI fusion, including AI frameworks and algorithms, what AI optimized models look like, and how to enable distributed processing, AI fabric, how to design for AI resource management, and how to do prioritization. AI microelectronics, including topics such as edge hardware and edge compute, and AI engineering, which is what I mentioned before, examining what it takes to deploy and monitor systems with justified confidence. How do we know we're doing AI right? AI engineering is our critical focus area and certainly takes into account aspects of AI fusion. And I'm looking forward today with our panelists to be talking about work in these important areas. I want to make one other quick note, which is that this is a collaboration conversation. Part of that means being in conversation with the audience. So please do ask questions. We'll be happy to get to those throughout the panel as well as at the end of our conversation here. So I'm going to stop talking and turn it over to our panelists. Let's start by having each of you introduce yourself and describe how your research and work connects to enabling AI systems in complex environments. Yuejie, we'll start with you, then go to Peter, then Matt.
Hi, everyone. My name is Yuejie. I'm a professor at the Department of Electrical and Computer Engineering here at Carnegie Mellon University. My primary research interests are in the theoretical and algorithmic aspects of machine learning, data science, signal processing, and inverse problems. So I have been coming on a long way until I come to this point in terms of research interests. In the old days, I work on actually very signal processing applications. My first project was actually on waveform designs for radar applications, for radar problems. But throughout the years, I have been more and more interested in machine learning because of the data deluge. And I'm very interested to see how some of these advances in machine learning can be translated into the practice of building actually artificial intelligence systems. Another focus of my research is to design efficient algorithms, particularly in resource-starved, resource-constrained environments where the resource constraints could be sample-starved environments where the sensors and imaging modalities can only collect a limited amount of data due to energy or power limitations. This resource constraints can also come from, say, if you are running something on a distributed platform and you may have some communication constraints across different sensors and different agents, how to design algorithms that can actually be communication efficient from a theoretical perspective. So with that, I'll pass on to Peter Hi,
I'm Peter Steenkiste. I'm a professor in the computer science department and in the electrical and computer engineering department at Carnegie Mellon University. My research area is networking, very broadly defined. So I've done research in more traditional internetworking type of network as we see it today. I've also worked on a variety of DARPA projects in the networking space. And I've spent a fair bit of time working on many aspects of wireless networking and more recently, edge computing, which is a way to basically deal with applications that don't have the time to wait for packets to travel long distances. So I'll leave it at that and pass it on to Matt.
Hello, everyone. I'm Matt Gaston. I'm the director of the newly formed AI division at the Software Engineering Institute at Carnegie Mellon University. I also have an adjunct appointment in the Institute for Software Research at CMU. I'm really grateful to be here today and be joined by my colleagues. I think it will be an exciting conversation. As far as what we're doing and where we're focusing our energy to realize AI systems in a reliable and responsible way, Really over the last 2 or 3 years, the Software Engineering Institute has been building up its capacity and advancing a research agenda on the topic of AI engineering, broadly defined. The way we think about it and shape our work in AI engineering is along 3 pillars that have been constructed based on feedback and input from our stakeholders across the defense and national security community, based on our collaborators that we work with at CMU, the faculty at CMU and beyond, and even from some industry partners and collaborators. Those 3 pillars are human-centered AI. What we mean by human-centered AI in the context of AI engineering is how to design, build, and operate AI systems with the intent and desires of their human users or counterparts in mind throughout the life cycle. How do you maintain alignment and trust from the design phase to the development phase and during and throughout deployment of these systems? The second pillar is robust and secure AI, where we worry about test and evaluation of these systems, methods and techniques for building robustness into AI systems, really knowing that these systems will operate the way they're intended, or at least provide as much evidence and justified confidence that they'll operate like they're intended to. And then the last pillar is scalable AI. And that, of course, means getting AI capabilities to work at the size, speed, and scale, size, speed, and complexity of mission applications or business applications. But also, how do you scale AI components to different form factors, different edge devices, where they might be deployed and used in interesting and novel ways? And then the last part of scalable AI is looking at how to scale AI in a responsible and reliable way across the enterprise. So what are the processes, methods, techniques that allow broad and responsible adoption of AI capabilities and use in a whole variety of different missions and applications?
Thanks so much, all. I'm really excited to dive in a little bit deeper. All of you talked about how your work relates, especially in resource-constrained environments, edge computing, the design of efficient algorithms, the principles of AI engineering. It's hard to do AI well. It's even harder to do AI well in resource-constrained environments, which is what we face in the defense and national security space every single day. So, but let me start off our conversation here by asking that, both AI fusion and AI engineering focus on enabling AI systems and optimizing operations to enable transition and scaling of AI solutions. Let's start by talking a little bit about the challenges. What are some of the challenges that you see standing in the way of that today? And Peter, maybe perhaps we'll start with you.
Sure, I'll be happy to do that. So I see a number of challenges that I think stand in the way in this broader space that you describe. So the first one is kind of exactly in my area, which is networking itself. If you're looking at where all the energy is traditionally going in terms of optimizing networks, both in academia and in industry, it focuses on things like the internet and data center networking. Those are really the 2 hot areas. And I can understand that there's a lot of money in these areas and it's a very widely used technology. But challenge networks are very different. So I think of those, or resource constrained networks are very different. So bandwidth is not, as cheap and readily available. And from a networking perspective, the topology of the network, for example, tends to be somewhat variable. How much bandwidth is available changes quickly over time. So optimizing the network is much more challenging. And so that is one of the problems that we're working on right now. At the very basic level, you want to get as many bits per second out of the network as possible. And so that's a different problem from optimizing performance of the internet, for example. But I think there are 2 other elements that are a little bit more specific to AI systems. The first one is that the way I like to think of this is that not all data is equal. Okay, so there are some data that is often of more value than other data. Some data has more of a deadline associated with it in terms of how long it is useful and when it should be delivered to be useful. And so when I look at AI systems, for example, they're very different from some of the systems we've been looking at in the past. So for example, a lot of the focus in the internet is on video. Well, we understand video very well. I mean, it is pretty, it's actually not that hard to understand how video works. With AI systems, this is much more complicated, right? Because it depends on not just the AI system itself, but also the application that uses the results from the AI system. You know, does it need to get geographic coverage in terms of the information it gains, or is it mostly interested in specific areas and so on? And so kind of coming up with network solutions that can consider these priorities of the applications as part of the operation, I think is very important. This is actually an old area of research that I worked in as early as in the 90s as part of a DARPA project. I think of it as kind of application-aware networking. So your network doesn't blindly optimize something; it kind of is aware of the priorities of the applications. So I think just figuring out exactly how to make that work in this kind of new type class of applications that has, significant bandwidth requirements. If you consider the use of sensor data, for example, I think is very important. The second change in technology is the availability of edge computing, which basically means that computing resources aren't centralized at a particular location somewhere, but they are potentially distributed throughout the network, and the properties of edge computing devices are likely to be different from the properties of cycles or compute cycles available in data centers. And so bringing that part of the system in terms of efficient resource use with applications in mind, I think is another important angle. So those are kind of at a very high level, the type of problems that I see kind of looking at bottom up at the whole AI system stack.
Thanks so much, Peter, for that overview. Yuejie, might you go next and talk a little bit about how you see the challenges from the algorithm perspective?
Yeah, sure. So I think that there's definitely a lot of challenges. I guess a major component of the question is about transition. So I see from both the horizontally and vertically, there are two ways to think about the problem. So one is if you think about for each subfield, say if I take computer vision as an example, I'll take speech processing as an example, there are lots of empirical successes that we see from publications, from academia, how to convert this singular success to another bigger domain, to a different problem, how to transfer this. This turns out to be not trivial at all. Many of the successful solutions we see for AI algorithms tend to be not being easily replicated if you convert it to a totally different environment, or even to a different data set, although the data may have similar features, but just because we are now collecting an entirely new data set, there may be some distribution shift so that the old algorithm may not you cannot replicate the nice performance of the old algorithm in this newly collected data set. So this just try to single out the difficulty of even within the single field, how to sort of replicate the success of AI algorithm to a new environment might be difficult. Another difficulty is if you look horizontally, to build an AI system, we actually need to combine many different pieces of subfields, not only computer vision, speech processing, natural language processing, but even go to the bottom, maybe hardware levels, or some of these networking levels, Internet of Things, how to actually bridging together these different pieces, leveraging the sort of state of the art across these different fields is another very big challenge that one needs to tackle in order to really scale up this AI system success. Some other ideas here is one thing I found interesting or sort of particularly challenging when we think about defense applications is we see lots of successes in the AI, particularly from the commercial side, where the successes are really built on part of spending out lots of data and computation resources. This may not be readily available for the type of problem we are interested in defense applications. The amount of training data could be significantly less due to the time that we can collect the data in natural environments. The environments could be much more adversarial and contested than sort of a commercial scenario. So how to actually get algorithms that can work in this resource hungry environments that develop algorithms require much less amount of data and computation is a key to scale up this AI solution. Finally, the last thing I want to mention is if we want to get all these different subfields to work together, often there needs some sort of common language, or at least some common metric of success. This tends to be actually quite difficult to get these days. Even there may be many people working on, say, maybe the same problems, say federated learning or distributed learning, but people in the algorithm and on the hardware end may actually thinking about completely different things when they're talking about the same buzzword. So this brings another challenge when we think about how putting all these people together to work on the common problem.
Thanks so much. We'll definitely come back to the piece that you mentioned on the common language just now, because I think that's so critical as we consider bringing all of these elements together. Matt, from where you stand, kind of what do you see as some of those main challenges?
Yeah, well, I want to say that I think the issues that Peter and Yuejie raise of networking and the movement of data and the prioritization of data in an application-specific context to the algorithms that we use to train these things, to the compute that we use to drive all of that. These are critically important, and there's lots of hard problems, and I think lots of great research questions in all of that. Sort of taking a step maybe up or back from those more bottom-up considerations. One way to summarize some of the things that Yuejie said, I think there's a huge difference in what happens at the model development phase in building of an AI capability, and certainly laboratory testing. A huge difference between those phases and then what happens in deployment. Almost always what is going on at model development time is models are evaluated on accuracy. How well do they perform the specific task that they're being built for? And when you deploy these systems, of course, there's other considerations. You might want to trade off accuracy for computational cost or accuracy for robustness, knowing when you're wrong or when you might be wrong or how you might fail or how you might be manipulated. And so I think this is one of the big challenges I see in sort of the broader adoption and the scaling of AI solutions, in that there is a huge difference between how these models are built and then what happens when they're integrated into a larger system and deployed in the real world, where they're met with changes that happen in the environment and the context around where they're operating. Stepping back even further, and I've talked to a lot of friends and colleagues in industry where they're doing amazing things with AI capabilities, but a lot of it is still based on craft, individual heroics or team heroics, where they work really, really hard for a long time to get these models, these systems to work in a way that drives business or drives mission. And it's not always repeatable. Yuejie mentioned the repeatability, maybe epidemic that there is in the machine learning community. And so I think there's a need for a shift from a craft and heroics to improve standards and improve discipline around how we build these systems, so that we can get towards better repeatability and knowing that the systems are operating the way we intend. Another topic, which I won't unpack too much here, is trust and trustworthiness. With the modern phase of AI, where most of what we're doing is, deep learning or at least modern machine learning, those systems are opaque. It's not clear why they're making the predictions or decisions that they're making, and there's lots of efforts, lots of research going on how do we increase trust, understandability, interpretability of these systems, which I think is also a barrier to scaling of these types of AI solutions. And then Rachel, because you're here and I'm sorry I didn't prepare you for this, I think you might have a few thoughts here on related to digital transformation and individual and organizational readiness when it comes to the use of these types of technologies. So I'll throw it back to you maybe for some comments.
Yeah, absolutely. I think from where I sit and the role I play in the organization here is to get us to recognize that technology alone can't solve our challenges. And that when we bring a new technology into an organization, it has implications for how we work, for how we need to organize teams, for what we're trying to accomplish. And, digital transformation is about adopting tools for stakeholder outcomes, oftentimes we get so enamored with the tools, we lose sight of what really are the outcomes that we're trying to achieve. And so I think what everyone outlined just now in terms of challenges, it speaks to, it's really hard to hold the complexity of all of this. You need to be looking at all of these individual component levels and then understanding how do we bring these together over time to allow us to achieve these desired outcomes that we as an organization have. And so that's the piece where, I think that I'm excited to shift this a little bit from well, it's still a challenge, I'll say that disclaimer, but one of the things we talk a lot about in AI engineering is about giving people justified confidence. We want systems we want to be able to close our eyes, cross our fingers and say, this is going to work, or at least that's the approach a lot of people are taking right now. And we need to shift that to being more confident that these systems will work over time. I thought that everyone brought up kind of key barriers to achieving this justified confidence in their opening comments, about challenges, what Peter mentioned on that not all data is created equal and people lose sight of that. Yuejie talked about that, transferring across domains is non-trivial, and oftentimes that it leads to those barriers in confidence. And Matt, of course, talking about that engineering perspective and why it can play a role in helping to enable it. So I just wanted to see if we could unpack this notion of justified confidence a little bit further and talk about what justified context looks like in the areas of work that you all do. And Yuejie, maybe we'll start with you on this one.
Yeah, sure. So I find it to be useful to maybe draw an example from some of my research experiences. So one of the area I work on is signal processing and radar application, or sort of navigation applications. And classically, as radar, sonar, and all this are very sort of critical environments and critical applications, people do need to have a lot of confidence in the solution that, the algorithm we design should have some sort of confidence. So what do we mean by confidence for those kind of classical models? Generally, we will have something like, say, receiver, some ROC curve. I'm sure a lot of the audience probably are aware of. It's a sort of receiver operating characteristics. So basically, it's a curve where if you want to set up some threshold, in terms of what kind of performance or false alarm risk you want to get, and then by reading off the curve, you know where to set your system, how to configure your system with confidence. And also we will have something like a confidence uncertainty quantification, in the sense we have an idea about if I want my solution to be, say, 90% correct, then how good my estimate is. So we typically have some idea about in terms of how good our estimate is, or the solution we get from the system from the statistical perspective. And these are very important to give us sort of the confidence, because we know the way we have configured the system in such a way, we know how likely it will fail based on our configuration. And the reason we have such configurations is typically because we are largely operating in a model-based regime where the system is designed based on some very well articulated mathematical model. And we have done lots of calculations and simulations to come to the solution that we have this confidence. Well, if we now compare this story with what we currently have in the AI age, it's largely missing because we now are operating in this data-driven regime where typically it's very hard to actually put down the similar type of confidence we have when we used to operate in this model-based regime and convert it to this data-driven regime. We are actually also lacking a lot of theoretical tools to do the same kind of calibration for the model we derive from, say, a black box machine learning system. So I think this is actually a very critical thing if we want to have justified confidence from the solution we get from the AI systems. We need to bring up some of this sort of capability that we used to have in sort of a classical engineering system to this modern AI systems.
Absolutely. Peter, Matt, either of you want to jump in and add?
Sure, I can comment on this. So, when I look at an AI system, it's basically a data-driven system in the sense that, there's collection of information, which is kind of happens at the infrastructure layer that I take care of. Then there's obviously algorithms, and then some kind of an application, which may involve people who need to make decisions, right, based on the output of the application. So, I have a fair bit of experience with optimizing data-driven systems, but they tend to be a little bit simpler than AI systems because I tend to understand the entire system, and that's not necessarily the case for AI. So I think of them as being three layers. So there's kind of like the application, the AI layer, and then there's the infrastructure, which is in my case more the networking infrastructure and some of the computational resources. I think that, if you're looking at justified confidence of the entire system, it is a very hard problem. And I think this is a new problem that really has to be explored. One solution that one might propose is we're going to make each layer meet the justified confidence requirement level, right? But I don't think that's really going to be enough. You can certainly think of many cases where you have a system with three components, and just because each component does the right thing doesn't mean that the whole system does the right thing. So I think we're going to need a little bit more than that. For me, there are one aspect of that is likely to be the interfaces between the components, things like basically providing information about how much data it is possible to collect. And so the AI layer can make more informed decisions about what information should be given priority to. AI algorithms may be able to provide some level of confidence, and confidence is probably too precise a term, but some level of, yeah, I'm pretty sure about that, as opposed to this may be silly. And so then obviously in the application is going to be highly application specific. I don't know how to deal with, but I think some notion of having interfaces so you can provide information, not necessarily just about confidence, but also other information that it might impact the confidence that in the other modules, I think is going to be important. And I don't, so I think it's a fascinating problem. And obviously it will require some interdisciplinary approach where you pick some use cases in terms of applications and then look at the whole system stack with people with expertise in different parts of the system. So I think it is important. So in the environment where I work, typically in context, there's different levels of justified confidence, kind of ranges from, yeah, I always have very good results, which is often not achievable, especially in resource-constrained environments. But at the very least, there needs to be some minimum bar that the system isn't going to do something outrageously wrong, right, or dangerous for that matter. So I think this is a very important problem, and is a very good way to kind of drive the system design, to be honest. So yes, I hand it over to Matt.
Thank you, Peter. I'll just add briefly. AI is certainly creating a lot of excitement right now, and everyone is interested in adopting and applying AI to their problems. It's important to remember that AI systems and AI engineering builds on a legacy of software engineering techniques and discipline of lessons learned from cybersecurity, systems engineering, and other fields. And we shouldn't forget all of the things that they've done. At the Software Engineering Institute, in the context of software and software reliance systems, we talk a lot about evidence-based assurance cases and how to produce them for different qualities that we expect in the software or the architecture of the software system. Again, those are really important, and they apply in the space of AI. Although AI does challenge the boundaries of how useful those techniques are. The three primary things that I see as challenges that come with AI are, as Peter said, they are data driven. In some ways, the functionality of a machine learning model is based on the data that's used to train it, or the observations that it makes to learn about the world. And so that data driving the behavior introduces a new level of complexity. They're often opaque, right? Deep neural networks are opaque and hard to analyze, certainly hard to reverse engineer and understand their functionality. Tools that help us do that will lead to better evidence production or justified confidence in making these types of assurance cases. And then third, they're inherently uncertain. And I know Yuejie mentioned uncertainty quantification, the idea that I may have a model that's 90% accurate, but it's only 60% confident in its predictions. How do we get a better match between confidence and prediction so that we know that the model is actually doing what we intend for it to do? And so with those three sort of challenges that AI systems, AI capabilities introduce into this larger system development environment, I think there's some things we can do that are both quantitative and qualitative. We did get a question about quantifying all AI qualities. Some of them are quantifiable today. We know how to do that. Some of them are harder to quantify, but there's still qualified analysis that can be done, or qualitative analysis that can be done. So I think it's important to pay attention to the data that drives these systems and where it came from, to do an analysis of that data, to look for things like bias, all the different forms of bias that exist, and how that data might evolve over time, even version controlling your data, because it does drive some of the functionality of the systems. It's also important to understand the methods that are used to train these models. It should be documented, well understood. You don't just want to take a model off the shelf or out of the GitHub repository and think, well, it's there, so it must be good, I can use it. Where did it come from? How was it used to, or what algorithms were used to train it? What features were used in evaluating that training? Was there more nuance than just accuracy, maybe accuracy and robustness, or all the other trade space that's possible? You can also look at how the model was tested and different aspects of that testing. Again, hopefully not just model accuracy. And then I think, as usually my comments sort of walk up the abstraction ladder as I go. I think these AI capabilities, what I would refer to as an AI model embedded in a larger system, should also have things like risk and failure analysis associated with them. What are the potential failures? Where is it appropriate to use these systems and not? And these are some of the more qualitative features, qualitative analysis that can be done with all of these systems. And then the last part, and I've mentioned it before, is ideas around interpretability and explainability. How much can the system share about the basis for decision making? How can that information be shown to its users, to its testers, the different constituents that are involved in the design and use of these systems? All of that leads to a compelling, justified confidence case. An important distinction maybe from how we think about traditional systems, especially in the defense context. It's not that we're going to test them and certify them as 100% accurate, 100% correct, and then they can go to field and they'll work forever in perpetuity at that 100% correctness level. But rather, how do we monitor and observe and analyze these systems throughout their deployment, throughout their life cycle, to make sure that they're performing at a level that is appropriate for that risk and failure and even use case analysis that I talked about.
Thanks, Matt. I really like that last point you made about that we can't get to a place where we have 100% confidence. It's about the paying attention over time. And, in this panel, all three of you are bringing really different perspectives to this whole systems design for AI systems. And so we have about 5 minutes left. I'm wondering if you each could talk about an example of trade-offs that you face in your work, particularly when you're thinking about resource-constrained networking environments, because I think that that's a key place where we want to have confidence, but we're going to navigate really hard decisions between aspects. So wondering if we could talk a little bit about trade-offs you encounter and kind of how you navigate them. Anyone's welcome to jump in. Peter, go for it.
Sure, I'll go. I've more or less hinted at this already, so this should be a short answer. The property of a resource-constrained system is since the resources that are available over time, changes, and it's a little bit more subtle than that, because a network has a geographic scope, right? So it connects different parts of a geographic region, and the resource distribution across this geographic area is going to be different and change over time. So it's actually a more complex problem. You can't just say 55% of the resources are there and now it's increased to 60%. That is too coarse-grained. So what is really necessary here is then helping in identifying what is the data, how much data can be made available, and what data can be made available, and what's the cost involved. Like, some data may be more expensive to collect because it needs to travel some weird path through the network or something like that. And so this really gets back to in some sense, getting right interfaces. Ultimately, the application values probably certain information, which is kind of what I think of as the output of the AI system, values different information differently. That needs to be propagated down to the AI system, which can then make decisions, hopefully, in the future at least, over what data is the most critical, and then this needs to be somehow combined, what is realistically feasible within the available resources. I'm obviously described this in an incredibly abstract way, but if you look at the basics, it's information, data, and bits, right? So, so I think that's one example where the trade-offs are effectively how much data and what data. Another parameter you have is accuracy of data. Certainly for certain types of data that's possible. One final thing I want to add is that once you have edge computing, it is actually possible to do some of the computing in the edge, reducing resource consumption, because the computing typically tends to reduce the volume of the data, right? And so that just adds an opportunity and a challenge, of course, in the sense that you need to make intelligent decision how you use that resource. So I'm going to stop here and give somebody else a chance.
Thanks, Peter. Yuejie, we'll go to you, and then Matt, you can offer a trade-off as a closing comment.
Sure. So I'll try to be brief because we are running short on time. I want just to highlight that I think theory is actually some of the basic research can be a very good solution to understand these trade-offs. In my own work, a lot of our research is trying to understand fundamental trade-offs of some of these basic quantities, such as how many samples you need or how much computation you need to do, and what is the quality of the samples you are collecting. Often, it turns out that from the theoretical perspective, there is indeed such fundamental trade-off that if you have more data, sometimes you can actually use less computation to get the same quality of solution. But if you only have very limited data, maybe you do need to spend more computation. So theory does provide you some sort of fundamental understanding in what can you do, what can you not achieve, no matter what type of algorithms you can design. So this can sometimes give you some sort of this negative message that your AI system cannot do anything you want, everything you want. There may be a fundamental limit, and no matter how you design your AI system, you cannot break this fundamental limit. So I think some of this basic research can be used to at least guide the practice in terms of gauging these different trade-offs in terms of resource availability in order to get some decision that we want to achieve.
So Rachel, knowing that we're out of time, I'll sort of summarize or conclude the same way that Steve Chen, who was a commissioner on the National Security Commission for AI, recently concluded a conversation we had. I'm just really excited that we're talking about trade-offs and thinking about this from an engineering perspective and how we balance across all of these different trade-offs. Accuracy, data size, data labeling, computational aspects, robustness, fundamental limits, as Yuejie mentioned. And I think as we learn more, we'll have an engineering discipline that allows us to figure out how do we navigate these trade-offs and build systems that work and operate in a reliable, responsible, and trustworthy way.
Thanks, Matt. And thanks all of you for joining our panel today. This is, as we really just did the tip of the surface for how complicated it is to really enable AI systems in complex environments. So if you want to engage with us further, please do reach out. We're working hard to think through some of these engineering challenges and would love to engage with all of you. Thanks, everyone.
The heart of the SEI is research, and our predominant objective is to help software practitioners learn SEI technologies, to help them in their work and to enhance software capability that's affordable, timely, and reliable.
some of the innovations that we came up with in terms of acquisition with the rest of the community are now new acquisition paradigms for the Department of Defense. And that goes all the way down to the cyber operators. We have great innovation in terms of how to do exercises and actually train our cyber operators for their day-to-day work. And our innovation gets used every day in that perspective as well.
When an innovation leads to something useful, it's the socio-technical knowledge and skills that allow us to successfully insert those innovations into programs, into the world.
And so the challenge at the SEI is to make sure that those innovations, even if they're not sexy, that they get enough attention paid, not just to the research itself, but also to getting it transitioned in the right way.
Everything changes when an innovation is adopted, right? I mean, some innovations become a ubiquitous part of everyday life, and some are just incredibly important for certain groups of people. But adoption means change. That's what it is at its core. And so I'm always excited by opportunities to escort an innovation from a small group of early adopters to a larger user population, and ultimately seeing that how that innovation lives and plays, because there's always a ripple effect. So seeing an innovation take root and become part of people's work is really rewarding.
What does Hello World look like for a weapon system? I mean, so granted, DoD and government have an awful lot of business IT systems. We have to run ourselves like a business, like businesses do. We have an awful lot of even software systems that aren't weapon systems necessarily, command and control systems, intelligence support, sure. A lot of that. And a lot of that's very appropriate to do a lot more rapid application development, right? Build a DevOps team that's got user representatives and operations and security all together working on it piece by piece. What does Hello World for a weapon system look like?
So I think if you think of it as a big, as a big monolithic structure, it's harder. But if you break it up into modules, then you can have Hello World for each of those modules, right? And I think that's the secret of doing it, in my opinion.
Yes, I think we haven't asked. We haven't asked for them to deliver us a weapon system that allows me to test the small changes. If I know in the future I'm going to make a change to this system and I can't get my hands on it, it's $1 million. I need you to provide me a system or a simulated environment that guarantees me a high level success, right? Something that's very close to that system that I can keep and I can work on. I think they probably have it in hand.
Yeah.
They've probably built it throughout their own companies. You just, as an acquirer of software, need to say, I would like to be able to test this also in my house where I'm going to operate it on.
Bringing all those people together from different places and different ideas really helps us form perspective, but it also helps us then spawn innovation across the community. right? We kind of become the seed or the germ of the innovation, and working with people over time, right? Whole industries are born.
We get great new ideas when we try to work across divisions. I think we get great new innovative ideas when we work with members of the software engineering communities and through our professional societies.
We have a collection of incredibly talented folks in their respective fields. And it's not just the researchers, as great as they are. It's the folks that do all the things that enable the researchers to do their jobs. We have some of the best and brightest in the various disciplines we all serve.
I support SEI staff by providing information that they need. I mean, we're not doing the technical work, but we're trying to understand it to the point where we can provide the resources for the technical staff to do their work. We learn a lot about the terminology, and it makes us better when we're developing search strategies.
Knowing that we have an SEI family that is made up of people from diverse backgrounds, educational backgrounds, cultural backgrounds, I think brings a lot to the table when you're tackling really hard problems for our sponsor.
Good ideas come from really bright people. And interestingly, one of the things that inspires me and keeps me focused on the work of the SEI is all of the really smart people we have here.
Although CI and CD play a huge role in the deployment pipeline, the foundation for a concrete application of DevOps practices requires the instantiation of a complete deployment pipeline before any application development is started. Having a complete deployment pipeline in place using infrastructure as code, configuration management, and provisioning technologies provides automation, which includes security, traceability, testing, and monitoring throughout the entire SDLC. These necessary services, in addition to a CI/CD service, include a local code repository, issue tracking system, wiki, code dependency manager, static code analysis utility, and an automated security testing tool. The functionality of each of these separated services can be automated by integrating them into continuous integration builds through various plugin platforms, such as the plugin community available for the Jenkins CI service.
Enterprise cybersecurity data, whether it's on your systems or in transit, is bigger and more varied than ever before. I hope you'll join us at FlowCon 2022 this coming January from the 11th to the 13th to see our presenters share new techniques and best practices for identifying diamond-in-the-rough insights, share their experience building machine learning models in a principled and methodologically sound way to support cybersecurity. You'll see talks that introduce novel situational awareness perspectives to observe attacker behavior, secure sensitive data, and manage risk in cloud deployments and on-prem. We all know network and system process artifacts can be far too many to store and analyze all in whole. Sometimes they're obfuscated by encryption. But our speakers from academia, industry, and government will share with you their research in contextualizing data and building scalable analytics and metrics to help you use your data to defend.
Many times people go out and buy point solutions, but they don't understand how we got there. And technology of itself you just can't place technology in an organization. There are a lot of other factors that are involved to include a culture change. So collaboration to me is being tightly coupled with our mission partners.
A benefit that we've had in our causal research of having a CMU staff or researcher participate is that our CMU collaborator who was applying causal search to cancer research data sets cut the roadmap in researching that cancer by like 6 years. The same technique was then shared with us to apply for use for our Air Force customer. So that's been really cool to see that research in a completely different domain within like 1 year made it over into our area, and we've learned from that. And that's now a standard approach for what we call feature engineering that we're doing.
I don't think people realize or appreciate how vital SEI research and expertise is to advancing national security in general and customer capability specifically. There have been numerous occasions during customer feedback sessions, for example, where customers have told me and a colleague of mine verbatim that we would not have been successful without the SEI.
I think SEI plays the role of catalyzing the software engineering community, bringing different parts of the DoD, bringing industry, bringing tech organizations together. When we can bring all these organizations together and work with us on some of the key challenges, it really opens up ideas and perspectives.
Next up is Dr. Tom Longstaff, SEI Chief Technology Officer. Today, he will be moderating the collaboration conversation, Implementation of the National Agenda for Software. This collaborative discussion will discuss and focus on SEI, DoD, research labs, and the software engineering community at large, and how it can help catalyze change that advances software engineering that will lead to more trustworthy and capable software resilient systems, as well as improve the state of the art and practices in software engineering. Stay tuned for the next collaborative discussion.
Welcome back, everyone. Thank you for hanging with us into what is going to be the last collaborative conversation of the day. This one is a really great conversation to close out on because we're going to catalyze change. We're going to take all the things that we've been hearing about for the last 2.5 days to 3 days and really focus it in on where do we go from here? You've heard a lot of technical discussions, a lot of very detailed technical research that's going on here. And I think I've got just the perfect panel for bringing this all together and really understanding how we're going to move from here. So let me briefly introduce our panel. First, I'd like to introduce Anita Carleton. She's our Director of the Software Solutions Division. She's in the executive leadership team here at the SEI, really leading the Software Solutions Division, where she spent more than 30 years of technical and senior leadership experience in the software engineering industry. The mission of SSD is to advance the state of the practice in software engineering through applied research, development, and transition of innovative technologies for building and acquiring software-intensive systems with the specific goal of making software a strategic advantage for the Department of Defense. SSD provides leadership through research collaborations with CMU and others in academia, directly engaging with major defense acquisition projects, partnering with industry, and informing DoD policymakers. Second one, Dr. Amy Henninger. Now, you saw her yesterday, and she's back for a return visit. She is the Senior Advisor for Software and Cybersecurity in the Office of the Director of Operational Test and Evaluation. Dr. Henninger has developed expertise at the critical intersection of computer science, information technology, advanced analytics, and the process of building strategic decisions at the enterprise level. Currently serving as a highly qualified expert, HQE, Senior Advisor for Software and Cybersecurity. Dr. Henninger formulates recommendations and strategic plans in software and cybersecurity for the Director of the Operational T&E, DOT&E. Finally, I lost my window here. There we go. Dr. Jen Roberts. A Maryland native, Dr. Jen Roberts is a visiting research scientist at the Applied Research Laboratory for Intelligence and Security, ARLIS, at the University of Maryland. Prior to joining ARLIS, Dr. Roberts served on the leadership team of the Defense Advanced Research Projects Agency, DARPA, as the Deputy Director of the Information Innovation Office from 2019 to 2021. So with these great panelists that I have in store here, where I'd really like to focus is a release that we had November 3rd, just last week, on a report called Architecting the Future of Software Engineering, a National Agenda for Software Engineering Research and Development. This is our 5 to 10 year roadmap of where we're actually going to be moving within research and engineering. So Anita, could I please turn to you first and give us just a short, brief synopsis of what is this report and what does it mean?
Oh, that's awesome. Thanks, Tom. I am so excited to talk about this report. The premise of the study is that the stakes for software are elevated now more than ever. It's the connective tissue to everything we do. Software engineering affects everything because software is everywhere. You hear a lot about our nation's infrastructure. Yes, software is all about that. Defense systems, financial systems, education and healthcare systems. And it's our ever-growing dependence on these software systems that really makes it imperative to maintain our nation's leadership and strategic advantage in software engineering. So in addition to devising a research roadmap that included a vision, research focus areas, and then a 5 to 10 year research roadmap for the future of software engineering, another key objective that we had was to really raise the visibility of software engineering to the point that it receives this sustained recognition and investment that's commensurate with other strategic priorities, such as AI, such as domestic chip manufacturing, or even the most recent discussions Ms. Xu made when she talked about hypersonics. So that's really the framing of the National Agenda Study.
So let me bring in, Amy and Jen on this as well, please. How important is a report like this for really catalyzing change in the future of software engineering and all of those kinds of things? Amy, can I turn to you first?
Yeah, absolutely, Tom. Thank you. So look, first I want to congratulate Anita and the SSD team on really superb work on the research agenda. So it was a brilliant reminder to me of SEI's thought leadership in this arena, and I think provided a really inspiring vision of where software engineering is going in the future and how critical it is to our national security and prosperity. Second, I wanted to note, and thank you for inviting me to join the panel. This is the second all-girl panel I've ever been on in my entire life, and thrilled to share the dais, the virtual dais, with Anita and Jen. You know, I can remember a time when I was in college in a class on software engineering where my professor taught us that a well-written requirements document will compile itself. I'm not going to tell you just how long ago that was, but let's just say it was before the manifesto came out. And so I grew up in a software engineering world, you know, that didn't have things like secure coding practices. It didn't have words like data science or digital engineering, or frankly, even the word cyber. So one of the things reading this document did for me was, beyond thinking about where we're going in the future, which it did spectacularly well, is it really gave me a chance to look back and reflect on where we've come from. And when you look at it from that perspective, it's really quite amazing. So I know we're going to get more into the research topics later, but I just really, you know, kind of an overview of the document. I think it's just a great retrospective of where we've come from, in addition to where we're going in the future.
Oh, thank you so much, Amy. Jen, how important is a document like this now?
Yeah, I think I would expand upon things that Amy has already mentioned, that it's useful for us to be able to reflect and also identify good thrusts for the future, right? And being able to identify areas in software assurance and security, et cetera, that really emphasize what we need to do in order to make the very vast software ecosystem that affects industry, affects the government, to be more not only secure, but work better for the people who are using it. It's very useful to have that kind of concurrence about directions that the community as a whole can pursue as we move forward.
Oh, thank you. That's superb. So I'm going to focus a little bit more sort of on the details and get a little bit of discussion going, hopefully, on some of these. I want to start with the vision. So the very center of the model is a vision that says humans and AI are trustworthy collaborators that rapidly evolve systems based on programmer intent. Amy, this sounds a lot like the sort of the early days where you made your prediction that's sort of coming out. Are we making a prediction again that is just something that's realizable?
Yeah, so that's a great question, Tom, and it hints on a couple of the things that I really liked about the report a lot, just beyond the research topics, which I know we're going to get into that model. And one of those is exactly to your point, this emphasis in automation and AI, right? So the notion that advancing software engineering is going to move us in this direction towards AI or in the AI space. And I really appreciated that because for many, many years now, and having worked at an AI company earlier in my career, I've defined AI personally as advanced software engineering, right? So 25 years ago, right, Deep Blue was AI, and now Deep Blue-like capabilities are things that, you know, I can play on my iPhone. 20 years ago, I can remember very, very specifically personal digital assistants, a huge research topic in AI. And I remember attending workshops with Milind Tambay, who used to be at USC, and I think he's moved on now, but who did great research in personal digital assistants. And now I can read this in the report that Anita and her team have issued and see, okay, now we're starting to look at the software engineering challenges of those. So I've always maintained that, you know, the boundaries of AI, the scope of AI, it's an evolving and moving target. As a society, we incorporate more of that technology into our daily lives. And I think that report really highlighted that. The other thing I really liked that somebody mentioned earlier was this idea of contrasting software engineering to other kinds of engineering. So, I think maybe we got a false start in the software engineering community. I think we tried to be too much like the civil engineers, like my little brother is, building bridges, and mechanical engineering, right, or astronautical engineering. And we failed to recognize that we don't have those long-term static problems like some of those engineering communities do. And that was another thing I thought this community, this report brought out, which I really appreciated, this notion that software is changing all the time, and we might need unique models and unique practices for how we apply software engineering principles. And then the last thing, again, to your point, I really, really appreciated this point of distinction between doing software and what software does. I thought that was highly appropriate, right? So joining DOT&E as a software advisor, I struggled very hard with what does it mean to do software T&E if you're an operational test person. And I came to the model where we'll actually have two sides of this coin, right? I have the art of testing software, and then I have to look at what software can do for testing. And then I saw that applied to the research, the R&E report that they sent back to Congress. They had this thing called a software S&T, and they ended up kind of using this model that you're putting forward too, saying, well, there's S&T for software and there's software to support S&T. So the fact that this agenda kind of had that same type of model gives me great confidence that the DoD got it right. And that's another tangential point, not the main research agenda, but I think really important points for us to provide that context to the research agenda.
Yeah, Anita, I know you want to jump in here, but what do you think in terms of how the vision is going to drive your future work within the SEI?
Yeah, I think that's a great question. There's a lot packed into that vision. There's a lot packed into the roadmap. I think there's a few very key considerations, though, I know that we had as we were thinking about this research roadmap. The first is that the whole software engineering pipeline's changing. It's accelerating the production of code and the ability to deploy software at high velocity. So we need to outpace our competitors' ability to rapidly deploy new computing capabilities that provably work. So you see a lot of those kinds of ideas in here with assurance, with AI augmented software development. But those are some important points. Another important consideration is that as systems get more complex, we need to think about smart automation. Amy mentioned that, but of every aspect of the software pipeline. So of course, that is going to inform a lot of our research. And then scale, and we talk a lot about scale, but scale motivates that need for safe and resilient software composition that is combining components to create large software systems. And you see a big focus on composability and understanding what the rules of composability are. And another consideration, because software is so ubiquitous, and I know Heidi Miss Yu talked about that on Monday, there's this ongoing and increasing need for software to continuously evolve to incorporate new capability, but that isn't enough. We've got to also understand how to continuously reassure software-reliant systems effectively without doing harm to existing capabilities. So what that means is that we have to elevate the importance of assurance evidence and assurance arguments. That's going to be a key as we think about research agendas. And then Amy talked a lot about AI. And so I think that's really critical. We're going to need to understand how to engineer systems that have AI components, but also how to apply AI across the whole software engineering lifecycle. And then I think the other really important thing that we talk about here is that we're going to need to consider new quality attributes. So for example, we'll need to think about data privacy and trust and ethics as increasingly important design considerations for societal scale systems like social media systems. And then really the last big consideration, Tom, that we had here is we also need to think about how we architect and engineer for new computational models, systems that have AI, people such as the social media systems I mentioned, and then multi-core and quantum. So those are some pretty big considerations, but all of these are going to play a really important role in our research agenda moving forward.
Well, that's a very aggressive and very broad set of implementation goals that you're going to do. Jen, how do you feel about this vision? Is this something you feel like we can carry into the future with this? Is this going to be something that drives the U.S. in the future?
So I think the parts that really draw my attention are some of the advanced development paradigms where we're trying to move from a point where by and large most of the development is done by a trained software developer and moving instead to a point where perhaps we write requirements for what we want our software to do, and we're having technology that provides assured, provably correct implementations, right? So there's a lot to that, right? And I think especially if we're thinking from a DoD or a US government perspective, there's a large repository of legacy systems that really would benefit from updating and increased assurance, increased integration. And practically speaking, the ability to have this assured composability and methods to really automate certain parts of the integration and the development process, those are necessary if we really want to be able to get where we're trying to go. So I think those are just a few of the parts that really grab my attention.
I'm really glad you actually brought assurance up, because I think one of the common themes we've heard across all 3 days is, whether you call it assurance or trust or trustworthiness or confidence, there was all of this evidence that says, how do we get to a future that incorporates this kind of a vision and be assured that it's going to do what we want the software to do? So I don't know who wants to jump into this first in terms of how do assurance arguments play into this?
Well, I'll jump in first. So I had the great pleasure of being a part of the DARPA SEI workshop that supported the development of this research agenda, and talked about all sorts of fascinating technologies, methodologies, formal methods, right? Assurance cases. And I found myself saying, because I was waving the DOT and E flag, right? I found myself saying, well, this sounds very developmental to me. How do I move this, translate it, transform it into a way that I can use it in DOT and E? So the difference for those who don't know, DT tends to be sort of more experimental and focused on verifying performance measures in some defined space and time, whereas OT, operational test, is more evaluative. And we look at system capabilities supporting operational missions with real warfighters across an operational envelope. So there's a really very clear line between what is technically testing software for DT versus OT. And the bottom line is, for OT, we don't test software, we test software-enabled systems. And that could be software-centric systems, that could be cyber-physical systems, but it's always in the context of a system and a mission and threats and a bigger mission environment. So to the point of the assurance case specifically, we don't do certifications, although it's very interesting and impactful test, right? So that would be something I would definitely want to keep my eyes on, because I do believe that in the future we're going to be able to mature enough as a community, an acquisition community, to be able to think of novel ways of really inserting that earlier into an OT thinking. Maybe not the actual certification necessarily, but the idea of where is that knee in the curve between what's really necessary to do a full-up OT on with a safety critical system, for example, and where in that spectrum can we accept more risk in the name of being timely and supporting operations in a relevant way? So that's a very interesting agenda item to me. Other ones though, and all of these are good. So everything on the research agenda is useful and beneficial to DOT&E because a stronger DT helps OT do better, right? So anything we do to improve DT will minimize the potential of finding flaws in OT when they're very, very expensive to find because number one, they're more expensive to fix. And number two, we've set up an entire operational environment to find them. So anything we can do to assure that software sooner is a great thing for OT&E. But the other topics that I found very, very interesting and sort of a more direct tie to development, to operational tests, was the whole idea of learning from operational data. For example, I mean, that was just a huge epiphany for me. The idea of continuous monitoring and sustainment. Of course, there were T&E practices for AI systems and the whole notion of automated self-healing and error correction. So I consider those like sort of closer to the DOT&E research agenda, but everything I considered relevant in the sense that it was going to be improving the software that would eventually get to OT&E or be OT&E'd over.
Yeah. Thanks, Amy. That's fantastic. Hey, we've got a couple of questions that have come in from our audience. So I want to start this one, and Jen, I wonder if you could weigh in on this. How can the national agenda for software engineering help encourage or focus industry investment in software engineering?
Right. So I think that identifying these themes that are at the edge of what's technically possible can help us build coalitions and find stakeholders across the industry who can break off different parts of this problem so that we can really make progress along the different thrusts to help update and improve and strengthen our software products.
Yeah, that sounds really good. It sounds like it's going to be interesting to see whether that really does encourage industry focus in that area or not. I see the promise, but I also see, potentially maybe saying not so much.
Hey, Tom.
Yes.
I wanted to just add something to what Jen said. I think it was in your kickoff Monday, Paul Nielsen in your kickoff on Monday morning or Monday afternoon. And there was this talk about res ops, that bringing sort of that kind of thinking. And the idea of res ops is, that there's rapid research to operations cycles between practitioners and researchers. It's really sort of taking DevOps and even moving to the left a little bit. But I think that is an important concept. If we could think about bringing that mindset to industry, to government, to academia, to build on what Jen said, I think to influence common investment by industry in some of these areas would really, I think, jumpstart this. And I think Ms. Hsu said something like, we need to look at what industry can invest in, and then for government focus, have new dollars where industry isn't investing. And so she was talking about the fact that we need to bring these common investments to address a common set of problems. And so I think that's going to be important too, as we think about how we enact and how we implement this research roadmap.
Mm-hmm. Anybody else want to weigh in on this one?
You know what? I'm just going to stomp what Anita and Jen said, Tom. I think by the very fact that SEI is a national leader in this space, and it's well understood by industry, at least the defense industry base, that you speak for and very closely collaborate with the DoD. I think this publishing this research agenda honestly gives at least the defense contractor base, their own roadmap for their IR&D programs to support the DoD in the future.
Fantastic. Well, I'm going to go to another question from the audience, if I could. So in the context of humans and AI working together to build software systems, can you comment on GitHub's Copilot, your AI pair programmer, and the opportunities and risks associated with this system? So what comes to mind here are in things like what we do in software laboratories like Kessel Run with pair programming. Could one of those be an AI?
Tom, I'm going to let others chime in as well here, but certainly, certainly that's a part of the vision that we are moving towards, things like that. So as we think about humans and AI working together and collaborating, I think your analogy to software factories and the kinds of collaboration and the kinds of work that are going on there, I think that's that could be a perfect environment to try out some of these kinds of collaborations. I mean, the thinking here is, what are the kinds of things that humans are best equipped to do and think about, and what are the things that AI can help? So trying to think a little bit about the strengths that both can bring to problem solving and advancing the agenda, I think is key here.
Yes, and then I would add on to that. I think there's already been promising work on the research side in programs like the DARPA Muse program,
Yes.
Looking at this type of programming. As we move in that direction, though, what we'll really need to think about is the software supply chain. Because you can imagine as AI, let's say it's combing through all types of GitHub code in order to make recommendations, we need to make sure that what code is being used to provide content for those recommendations is actually secure pieces. So there does need to be some type of filter in place and some type of automated checks that get to these assurance pieces so that we are really picking the best implementations and the most secure ones and making sure that our supply chain improves the quality of the software as we're moving forward.
Oh boy, and we just got a really, I think, key question in from the audience that I'd really like to hear all three of you talk about a little bit. How do we ensure alignment of the national agenda across DoD? Any ideas on how to initiate collaboration within DoD, OGA, Army, such as AFC and industry? And in general, how do we get enough collaboration to really make an agenda like this take off? Let's start with you, Amy.
Oh.
So sure, I have to laugh a little bit because when I used to work in the Army, I was on the Army staff for my first HQE job, actually. People used to tease and say, well, which Army are you talking about? So vision, Sean, is it? And a good question. Not an easy question to answer. So often the cultural questions are more challenging than the technical questions. I think anything to be successful in the building and the DoD writ large requires dogged persistence and a long-term view. There used to be a time in OSD before I got there, so I'm old, but I'm not that old, where there were software engineering offices all over OSD, and maybe that kind of organizational construct would move this along further and faster.
Yeah, excellent. I think you're exactly right. The culture is always the hardest of all the issues, as difficult as the research is. Anita, what do you think?
Mm-hmm. Well, I wanted to build off of Ms. Shu's talk on Monday because I think she's got a sense of urgency to really think about the future of software engineering and to bring the best technology and the best technology solutions. And there was something that she talked about that I think is helping, that I think can help us in to move to the right direction, which is that she talked about this rapid defense experimentation reserve funding, the radar funding. But the idea there is something that's really awesome to bolster, I guess, joint experimentation, enhance research labs and test infrastructures, bring different FFRDC teams together. But the idea is that we're bringing different parts of the community together to work on some of the toughest problems that are facing our nation. So I think that kind of funding moves us a step in the right direction to bring all different perspectives and bring, the best ideas, the best technology solutions, so that we can work on advancing the research agenda.
So Jen,
Yes.
question to you.
Yeah. And then building upon that, so I'm a huge proponent of pipeline models where you're connecting what's happening in the R&D community with what the operational needs are. So one of the, big challenges that face us in the software development sphere is how we're able to move new prototypes on the research side into some type of practical use, and how do we do that quickly? It's further exacerbated by the complexities of things like DoD contracting and the separations of different agencies and services. So really, there's, practically speaking, with the way that the DoD is structured, what we need is to build these coalitions, these partnerships across multiple organizations that create these pipelines to move from research prototypes into operations very, very quickly. Now, there's a number of ways that you can foster that. I know data was something that folks had hit on earlier. So having shared data that can be used across both the R&D and the acquisition side part of the community, right? So more of the operational community to facilitate both maturation of technology as well as test and evaluation. That becomes really crucial for acceleration. And then also just having steady partnerships where instead of thinking, well, I'm going to go and I'll create this prototype and then I'll try and push that through as a single entity, we're instead breaking that up and saying, well, here's the additional features or modules, and I'm going to have a continuous pipeline of capability going from the R&D side into the operational side. And I'd like to call attention to one collaboration like that, that might provide an exemplar. So this would be one between US Cybercom and DARPA called Constellation, where they're working to pilot just that type of pipeline.
Well, believe it or not, we are almost out of time. Boy, the time really flies fast on a thing like this, but I want to leave you all with just one sentence each on what is the most important to do right now to catalyze change. So Jen, let's start with you. What is the most important thing to do right now to catalyze change?
In my view, creating more of these pipelines to be able to move from R&D into operational context quickly, that's the key. Because as we start having this ability to prototype something and get it fielded, that opens the aperture for a huge amount of innovation that we can actually take advantage of in the real world. And then the rest of the wonderful research goals should follow naturally if we can make those pathways function well.
Excellent. Anita.
Tom, you're going to like this because this is the theme of this whole event, collaboration. But what I guess what I'm getting at there is I was thinking about how awesome it was to work and engage with the community, the software engineering community, to work on this research roadmap. Last year, when we partnered with DARPA to host the Software Engineering Grand Challenges Workshop, bringing the different perspectives, getting a sense of what the grand challenges were, I think was key. It's great to see now that the Department of Energy is moving forward this December and hosting a workshop and thinking about the scientific software engineering challenges. So I think for me, it's convening and enabling inter-community discussions and bringing different parts of the community together to work on these research focus areas.
You're right. I do like that one a lot. We are just about out of time. Amy, you've got the last word. What should we do right now? Amy, I think we've lost your audio.
I've got it. Are you good?
Yes.
Yes.
I'm going to be very quick here. So people understand already the emphasis on shifting left in the acquisition processes. What this research agenda did for me was it gave me permission to shift right. And to me, that's the collaboration that I need to take back to DOT&E to enact. It's very insightful, and I appreciate the opportunity to have read it.
Excellent. Well, I am extremely grateful to all three of Jen, Anita, and Amy. Thank you so much for sharing your insights with us and helping us sort of wrap the final session of the 3 days. And again, thank you to those of you in the audience for your questions and for your attention. And we will see you shortly for the wrap up. Welcome back to our closing session. What a just a fantastic 3 days on the research review. I hope you really enjoyed all of the work and effort that was put into trying to give you a real sense of where the Software Engineering Institute is with regard to its research agenda in software, cyber, and AI. Today, we really did focus on that future of AI, with AI engineering, with all about sort of the idea of confidence, and then finally in our last session that we just finished on the future of software engineering itself. I think the main theme today that we kept hearing over and over in a variety of forms was trustworthiness. How do you make things trusted? How do you actually create trust within these various areas? And whether it was through confidence, whether it was through making sure that we had robust AI, or making sure that we understood things like drift so that we could predict the actual performance of our AI systems, all of this comes back to just how difficult it is to build that level of trust in the future of AI technology so that we can rely on it, and rely on it both to create our software and to run with our software. And then, the panel that we had with Matt on AI engineering, sort of coming into this final portion of this, really gave us an indication of just how many hard problems there are still to solve in order to make all this happen. So the research is rich and effective and moving forward, and just, getting really excited. I want to just finish out by saying that throughout these 3 days, we had this whole idea of study, make, and transition, which really forms 3 lines of effort for us. But they all come together in collaboration into this nexus that says, without you and without all of these in together, we don't make the kind of progress that we need to make. So I'm asking everybody out there, for you, for the people in the SEI, for the people at CMU, in the private sector, in the government, work with us to create this future. The future that we just heard in this final pattern, in this final collaborative conversation, just won't happen without you. And so we just need that level of collaboration. It was all about sort of what's happening here. I want to, basically thank everybody who was involved in making this 3 days happen. All of our principal investigators, the researchers at work, really making all this happening. All of the people who made the presentations you see really shine, the graphics, the music, the back end, the production, the work that sort of happened in order to produce this show and sort of get it out there for you so that you could really get a sense of our research and open it up for you to be able to collaborate with us, was literally a work of hundreds of people coming in to make this happen. So I really want to make sure I thank all of you at the SEI. I thank all of you that were our external collaborators that participated with us. Learn more on our website. Look for our podcasts. Look for us on YouTube. Follow us on Facebook, Twitter, and LinkedIn. And with this, I'm going to turn my role over to the Director and CEO of the Software Engineering Institute, Paul Nielsen.
Well, thanks, Tom. And let's have no more PowerPoint. I think we've done enough PowerPoint in these last 3 days, haven't we? First off, let me just start by thanking Tom. Oh my gosh, Tom, you've done such a wonderful job of leading this effort, of putting together a really rich, I call it a rich and poignant review. I thought it was just super. You composed a review that presents SEI's research across the board in software engineering, cybersecurity, AI, and even some of the other emerging technologies out there like quantum that's so important. You can tell by my hair, I've been around a while, and my lack of hair. And I've attended a lot of reviews, conference symposia, and workshops over my career. And still, each time I go into one of these, I go in with excitement and anticipation of what I'm going to learn, what ideas I'm going to get out of what I hear, and what old friends and new friends I'm going to meet. A little harder in a virtual sense, but still I look forward to that. I leave each event like this recharged and recommitted to advancing the state of the art, the state of the practice, and how important it is, as Jen Roberts said, to transition this work into operations, because our work's really not done unless we can transition it as well. I also leave each event like this with a great wonder and appreciation for the bright women and men who bring so much innovation, dedication, and passion to their work. This review certainly was no exception to that. I was impressed by the breadth and the depth of the work that was presented and how broadly applicable it is to the needs of the defense community in particular, but also to the broader global community in general, because these are problems sort of like climate change that are problems that we all face all together. Software engineering, cybersecurity, and AI are really foundational technologies for almost all the technologies of the 21st century. I think Anita commented on that too, and that's really true. So I'm going to join Tom in thanking the featured presenters for sharing their work and their passion with us, as well as to all their colleagues at SEI, at CMU, from our customers and collaborators who contributed to this work, but maybe weren't on the screen. In addition, as Tom pointed out, there are a lot of people working behind the scenes on this to make a review like this a success. So special thanks to the tech writers, the graphics professionals, the IT pros, the production teams, the reviewers, the admin support, and the list goes on, who work so hard without being in front of the cameras. And finally, to our sponsors, to OSD, to many customers throughout the services and throughout the federal government, to our clients, our attendees, and our fans, thank you for your continuing support and the energy that you bring to our work, the innovation you bring to our research, and the relevance you bring to our efforts to make sure they're really connected to things that we need. You know, it's so important to be coupled to what is really needed in the world. As we close, please know that SEI's women and men look forward to working with you in the future, to solving the toughest problems you know about now, and also to anticipating the challenges yet to come. And even more importantly, to being your trusted and valued colleagues. So thank you very much. And to all the veterans out there, a special thanks, because I know tomorrow's Veterans Day, and we appreciate all the work that you've done for us and making us safe. Thank you so much.